The universe is a complex structure made of energy, matter, and many unexplained phenomena. Each level, from the smallest quantum particles to the largest cosmic structures, reveals new information about existence. Scientists have spent decades studying these levels, and every discovery brings new questions about space, time, and the nature of reality. These 7 levels represent the main stages of the universe's structure, beginning with the subatomic world and extending to the vast multiverse. So, settle in as we explore the 7 levels of the universe. At the smallest scale known to science, beneath the structure of every atom, there exists a realm so strange and so unlike anything we see in the everyday world that even the most brilliant minds in physics continue to find it mysterious. This is the subatomic level, a world of unimaginable smallness, where the familiar laws of classical physics cease to function as they do in our ordinary lives. Here, the rules that govern matter and energy behave in ways that seem to defy logic, where particles can exist in 2 places at once, appear and disappear, and even communicate across vast distances instantly. It is the world of quantum physics, a realm that has revolutionized our understanding of the universe and continues to challenge our deepest ideas about what reality truly is. To understand this world, we must begin with what makes up ordinary matter. Every object we can see, touch, or hold is made of atoms. Atoms themselves are incredibly tiny. One would have to line up about 100 million of them to cover the width of a single human hair. For centuries, scientists believed that atoms were the smallest possible units of matter, indivisible and indestructible. In fact, the word atom comes from the Greek word atomos, meaning uncuttable. But as human understanding advanced through experiment and observation, scientists discovered that atoms were not fundamental at all. They could be broken down into even smaller particles: protons, neutrons, and electrons. These 3 basic particles are what give an atom its structure. The protons and neutrons cluster together tightly in the center, forming the atomic nucleus, while the electrons whirl around them in vast regions of empty space called electron shells. The scale difference between the nucleus and the entire atom is staggering. If the nucleus were the size of a marble, the whole atom would be as large as a sports stadium. Most of the atom, therefore, is empty space, yet that empty space, bound by invisible forces, creates the solid world around us. The proton carries a positive electric charge, the electron carries a negative charge, and the neutron has no charge at all. These charges determine how atoms interact with one another. Opposite charges attract, while like charges repel. This simple rule explains why electrons are held close to the positively charged nucleus by the electromagnetic force, and also why atoms can link together through chemical bonds to form molecules. But even this picture of atoms as neat little solar systems with electrons orbiting like planets is far too simple. In the early 20th century, a revolution began when physicists such as Max Planck, Albert Einstein, Niels Bohr, and Erwin Schrödinger discovered that at the subatomic scale, nature does not behave in the smooth, continuous way we experience in daily life. Instead, energy and matter appear in discrete packets, or quanta. This discovery gave birth to quantum mechanics, a branch of physics that describes the behavior of particles smaller than atoms with astonishing accuracy, yet also introduces strange effects that seem impossible from the point of view of classical physics. One of the strangest ideas in quantum mechanics is called superposition. It means that a particle, such as an electron, can exist in multiple states or locations at the same time until it is observed or measured. In the macroscopic world, this sounds absurd. After all, a car cannot be in 2 places at once. But at the quantum level, particles behave according to probabilities rather than certainties. An electron is not located at a single point in space. Rather, it exists as a cloud of possibilities, described by what is called a wave function. When an observation or measurement is made, the wave function collapses, and the particle appears in one definite location. This idea challenges our most basic assumptions about reality, forcing us to ask whether the act of observation itself determines the outcome of events. Another mind-bending phenomenon is quantum entanglement. When 2 particles become entangled, their properties become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. This seems to imply that information can travel faster than light, which contradicts Einstein's theory of relativity. Einstein himself called it spooky action at a distance. Yet despite how bizarre it sounds, entanglement has been repeatedly confirmed through experiments. In modern physics, it has become the foundation for revolutionary technologies such as quantum computing and quantum cryptography, which could transform the future of information processing and security. As scientists probed deeper into the structure of matter, they discovered that even protons and neutrons are not fundamental particles. In the 1960s, experiments at high-energy particle accelerators revealed that protons and neutrons are made of even smaller constituents called quarks. Quarks are bound together by particles known as gluons, which act as carriers of the strong nuclear force, the force that holds atomic nuclei together. Unlike electrons, which can move freely around the nucleus or even between atoms, quarks are never found in isolation. They exist only in combinations. 3 quarks form a proton or neutron, while quark-antiquark pairs form particles called mesons. This peculiar behavior of quarks is a consequence of a principle known as color confinement, described by the theory of quantum chromodynamics. The discovery of quarks and gluons was a major step forward in the quest to understand the building blocks of the universe. But scientists did not stop there. They identified many other particles that appear only under extreme conditions or in high-energy collisions, such as those produced inside particle accelerators like the Large Hadron Collider. These particles include muons, neutrinos, bosons, and many others that make up what is known as the Standard Model of particle physics. The Standard Model, developed over decades of research, is one of the most successful scientific theories ever constructed. It describes how all known particles and forces except gravity interact with one another. According to the Standard Model, there are 12 fundamental matter particles divided into 2 families, 6 quarks and 6 leptons. Quarks come in 6 flavors: up, down, charm, strange, top and bottom, while leptons include the electron, muon, tau, and their associated neutrinos. In addition to these matter particles, there are force-carrying particles called bosons that mediate the fundamental forces of nature. The photon is responsible for electromagnetism, the gluon for the strong nuclear force, and the W and Z bosons for the weak nuclear force. In 2012, the discovery of the Higgs boson at CERN completed the Standard Model by explaining how particles acquire mass through interaction with the Higgs field. Despite its success, the Standard Model is not the final answer. It does not include gravity, which is described separately by Einstein's general theory of relativity. Gravity is extremely weak compared to the other forces at the subatomic level, yet it dominates on cosmic scales, shaping planets, stars, and galaxies. Uniting quantum mechanics and gravity into a single framework has been one of the greatest challenges in modern physics. Theories such as string theory and loop quantum gravity attempt to bridge this gap, proposing that the fundamental particles we know are not truly point-like, but rather tiny vibrating strings or loops of energy existing in higher dimensions beyond the 3 we perceive. At the subatomic level, everything that seems solid and continuous in our macroscopic world dissolves into a dance of energy and probability. Even the distinction between matter and energy becomes blurred. According to Einstein's famous equation, E just mc2, mass and energy are interchangeable. A small amount of mass can be converted into a tremendous amount of energy, as demonstrated in nuclear reactions that power the sun or in the destructive force of atomic bombs. Conversely, pure energy can transform into particles of matter under the right conditions, such as those present moments after the Big Bang. The subatomic world also reveals the dual nature of particles and waves. In experiments like the double-slit test, light and electrons can behave as both particles and waves depending on how they are observed. When not measured, they produce interference patterns like ripples on water. When detected, they appear as individual particles. This wave-particle duality is one of the central mysteries of quantum physics. It tells us that particles are not tiny billiard balls, but quantum objects that follow a completely different logic, one where potential and probability define existence itself. One of the most intriguing subatomic particles is the neutrino. These are nearly massless particles that interact so weakly with matter that trillions of them pass through every human body every second without leaving a trace. They are produced in enormous quantities in nuclear reactions inside stars, during supernova explosions, and in human-made reactors. Because they rarely interact, Detecting them is an enormous experimental challenge, requiring vast underground detectors filled with special materials to capture the faintest signs of their presence. Another fascinating particle is the muon, a heavier cousin of the electron. Muons decay very quickly, but they have played a key role in testing the limits of the standard model. Recent experiments have suggested that muons may behave slightly differently than predicted, hinting at the possible existence of new physics beyond our current understanding. At the subatomic scale, forces do not act in the simple ways we experience in daily life. Instead of being transmitted through direct contact or invisible fields, they are mediated by the exchange of particles. When two electrons repel each other, for example, what is really happening is the exchange of virtual photons. In a similar way, quarks inside protons and neutrons exchange gluons to remain tightly bound. These exchanges happen so rapidly and at such small distances that we never perceive them directly, yet they govern every interaction in the universe. Even the concept of empty space loses its meaning at this level. What we call a vacuum is not truly empty. It seethes with energy and virtual particles that constantly appear and vanish in unimaginably short timescales. This restless activity is known as quantum fluctuations. These fluctuations have real effects, influencing phenomena such as the Casimir effect and the tiny variations in cosmic microwave background radiation that gave rise to galaxies billions of years later. The study of subatomic particles has also revealed that matter as we know it makes up only a small fraction of the universe. Observations of galaxies and cosmic background radiation indicate that ordinary matter accounts for less than 5% of the total energy content of the cosmos. The rest consists of mysterious substances called dark matter and dark energy. Dark matter exerts gravitational effects that hold galaxies together, while dark energy drives the accelerated expansion of the universe. Despite decades of research, the true nature of these components remains unknown, suggesting that there are still undiscovered particles or forces at play beyond the standard model. To explore these mysteries, scientists use particle accelerators, massive machines that propel particles to near the speed of light and smash them together. By studying the resulting debris, physicists can infer the properties of particles that exist only fleetingly before decaying. The most powerful of these machines, the Large Hadron Collider, operates at CERN near Geneva and spans a circumference of 27 kilometers. It was instrumental in discovering the Higgs boson, but it continues to search for evidence of supersymmetric particles, extra dimensions, and other phenomena that could point toward a more complete understanding of nature. At the subatomic level, time and space themselves behave differently. According to quantum field theory, every particle is an excitation of an underlying field that extends throughout the universe. These fields are the true fabric of reality, and particles are simply localized ripples within them. For instance, the electromagnetic field gives rise to photons, and the Higgs field gives particles their mass. This view replaces the classical idea of particles as tiny solid objects with one in which everything is interconnected through continuous fields of energy. This new perspective also implies that even the vacuum of space possesses energy, a concept known as zero-point energy. Though it cannot be easily harnessed, zero-point energy is believed to play a crucial role in the universe's evolution, possibly linked to dark energy itself. The recognition that empty space is filled with invisible activity has completely changed the way physicists understand existence, transforming what once seemed like nothingness into a dynamic sea of quantum potential. One of the greatest philosophical implications of quantum mechanics is that the universe at its most fundamental level appears to be governed by probability, not certainty. Before measurement, particles do not have definite positions or velocities. They exist as potentialities. Only when we observe them do they take on specific values. This has led to countless debates about the role of consciousness and observation in shaping reality. Some interpretations, such as the Copenhagen interpretation, suggest that the act of measurement collapses the wave function into a single outcome. Others, like the many worlds interpretation, propose that every possible outcome actually occurs in separate parallel universes. Quantum mechanics has not only transformed our understanding of nature, but has also given rise to practical technologies that shape modern life. The principles of quantum physics underpin lasers, semiconductors, magnetic resonance imaging, and even the transistors that power every computer and smartphone. The next great leap forward may come from quantum computing, which uses quantum bits, or qubits, that can exist in multiple states simultaneously. This allows quantum computers to process information in ways far beyond the capability of classical machines. The next great leap forward may come from quantum computing, which uses quantum bits, or qubits, that can exist in multiple states simultaneously. This allows quantum computers to process information in ways far beyond the capability of classical machines. In the coming decades, quantum technologies could revolutionize fields from medicine to cryptography and artificial intelligence. Yet, the more we learn about the subatomic realm, the more questions arise. What is the ultimate nature of reality? Are space and time truly fundamental, or do they emerge from something even deeper? Could the universe itself be a vast quantum system where everything is entangled across cosmic distances? These questions push the boundaries of both science and philosophy, reminding us that our understanding of existence is still incomplete. Even the forces we know may not be the only ones that exist. Some theories propose the existence of a fifth fundamental force that could explain the behavior of dark matter or the anomalies seen in certain experiments. Others suggest that the constants of nature, such as the speed of light or the strength of gravity, might not be fixed, but could vary across space and time. Such ideas challenge the very foundation of physics and demand new ways of thinking about the universe. In many ways, the study of the subatomic world is a journey backward in time. By probing deeper into the nature of matter, scientists are uncovering conditions that existed in the earliest moments after the Big Bang nearly 14 billion years ago. In those first fractions of a second, the universe was an unimaginably hot and dense soup of fundamental particles. As it expanded and cooled, quarks combined to form protons and neutrons, which then fused into the first atomic nuclei. Eventually, electrons joined these nuclei to form atoms, giving rise to the stars and galaxies we see today. By recreating these high-energy conditions in laboratories, physicists can glimpse the processes that shape the universe itself. Ultimately, the subatomic level is more than just a scale of measurement. It is the foundation upon which all matter, energy, and structure are built. It reveals that everything, from the smallest grain of dust to the largest galaxy, is composed of the same fundamental ingredients, governed by the same universal laws, and yet, these laws operate in ways that are often counterintuitive, unpredictable, and deeply mysterious. The universe, at its core, is a vast quantum symphony of particles and forces, constantly in motion, constantly interacting, and constantly evolving. The deeper we peer into this invisible world, the more we realize how little we truly know. Every discovery opens the door to new questions, and every experiment hints at deeper layers of reality yet to be revealed. What lies beyond quarks? Are there substructures even smaller, perhaps strings vibrating in the 11 dimensions as some theories propose? Or is there a limit, a smallest possible scale where space and time themselves dissolve into pure quantum foam? Whatever the answer, the study of the subatomic world continues to redefine our understanding of existence. It reminds us that beneath the solid surface of reality lies a universe of ceaseless activity, governed not by certainty but by possibility. At the heart of every atom, within the tiniest flicker of energy, we find the same mystery that has driven human curiosity for millennia, the desire to know what everything is made of and why it exists at all. Topic: atomic and molecular level. Atoms and molecules are the basic parts that make up everything around us, and the way they interact with each other decides how different substances behave. The atomic level represents one of the most fascinating and fundamental layers of existence. It is the scale at which everything we see, touch, breathe, and even think about is built. Every object in the universe, from the air around us to the stars shining millions of light years away, is made up of atoms. An atom is the smallest unit of a chemical element that still keeps the identity and behavior of that element. When we talk about atoms, we're talking about the foundation of all matter, the invisible bricks from which every substance in the cosmos is formed. To understand the atomic level is to understand the very structure of reality itself. An atom may be unimaginably small, but its internal design is both elegant and complex. Inside this tiny structure lies an entire world made up of even smaller particles, known as subatomic particles. These are the proton, the neutron, and the electron. Together they form the atom's basic framework. The protons and neutrons sit tightly packed at the atom's center, in a region called the nucleus, while the electrons move rapidly around this center in regions called shells or energy levels. Although the atom seems simple in concept, it contains layers of mystery that scientists have studied for centuries and continue to explore even today. To understand how small an atom truly is, one must step beyond ordinary imagination. If a single atom were enlarged to the size of a football stadium, the nucleus at its center would be no larger than a small marble sitting in the middle of the field, while the electrons would be spinning around at the outer edges of the stadium. Most of the atom, therefore, is actually empty space. This emptiness, however, is filled with invisible energy fields that hold everything together. This strange structure allows atoms to form bonds with each other and create the endless diversity of matter that we observe in the world. The nucleus is the heart of the atom, and it contains most of its mass. The protons inside the nucleus carry a positive electrical charge, while the neutrons are neutral. They have no charge at all. The number of protons in an atom determines what element it is. For example, hydrogen, the simplest element, has only one proton in its nucleus. Helium has 2 protons, lithium has 3, carbon has 6, oxygen has 8, and uranium has 92. These numbers define each element's identity, just like a fingerprint defines a person's identity. No matter where it is found in the universe, an atom with 8 protons is always oxygen, and will always behave like oxygen. Surrounding the nucleus is a vast cloud of electrons. Electrons are much smaller than protons or neutrons, and carry a negative charge. Because of this opposite charge, the electrons are attracted to the positively charged nucleus, just as the planets are held in orbit around the Sun by gravity. However, electrons do not orbit the nucleus in neat circular paths like planets do. Instead, they move in complex patterns within areas known as orbitals, which represent regions where each electron is most likely to be found. The electrons occupy specific energy levels or shells around the nucleus, and each shell can hold only a certain number of electrons. When the outermost shell of an atom is filled, the atom becomes stable. When it is not, the atom tends to form bonds with other atoms to reach stability. An atom's behavior, how it reacts, bonds, and interacts with others, depends mainly on how its electrons are arranged. The outermost electrons, called valence electrons, are responsible for chemical bonding. For example, an oxygen atom has 8 electrons, 2 in the first shell and 6 in the second. Since the second shell can hold 8 electrons, oxygen needs 2 more to complete its outer shell. This is why oxygen tends to form 2 bonds with other atoms. It is seeking stability by filling its outer shell. This simple rule of electron arrangement explains the chemical behavior of all elements and how they come together to form everything from water and air to DNA and steel. If we look deeper into the structure of the nucleus, we find that protons and neutrons themselves are not indivisible. They are made of even smaller particles called quarks, which are held together by another type of particle known as gluons. Quarks and gluons belong to the world of quantum physics, where the laws of nature become extremely strange and unpredictable. At this level, particles behave both like solid matter and like waves of energy. They can exist in more than one place at the same time, disappear and reappear, and even affect each other instantly across vast distances. This quantum behavior lies at the heart of everything that happens inside an atom and is the key to understanding how matter and energy are connected. The concept of the atom has a long and fascinating history. The word atom comes from the ancient Greek word atomos, meaning uncuttable or indivisible. Over 2,000 years ago, the Greek philosopher Democritus proposed that all matter was made of tiny indivisible particles. Although his idea was mostly philosophical at the time, it turned out to be remarkably accurate. However, it wasn't until the 19th century that the atomic theory became a solid part of science, thanks to the work of John Dalton. Dalton suggested that each element is made of identical atoms and that chemical reactions are simply the rearrangements of these atoms. His ideas laid the foundation for modern chemistry. As science advanced, new discoveries revealed that the atom was not indivisible after all. In the late 19th century, the English physicist J.J. Thomson discovered the electron while experimenting with cathode rays. He realized that these rays were made of tiny, negatively charged particles that were much smaller than atoms. This discovery showed that atoms had internal structure, which was a revolutionary idea at the time. Thomson proposed a model of the atom known as the plum pudding model, in which electrons were scattered within a positively charged substance, like raisins inside a pudding. However, this model was soon replaced by a more accurate one, thanks to Ernest Rutherford. In the early 20th century, Rutherford conducted a famous experiment where he shot alpha particles at a thin sheet of gold foil. He expected them to pass straight through, but to his surprise, some particles bounced back. This led him to conclude that the atom must have a tiny, dense, positively charged centre, the nucleus, surrounded by mostly empty space where electrons move. This discovery changed the way scientists saw the atom and laid the groundwork for nuclear physics. Later, Niels Bohr refined Rutherford's model by introducing the concept of quantized energy levels. Bohr proposed that electrons move in specific orbits around the nucleus and that they can jump between these orbits by absorbing or emitting energy in the form of light. This idea explained why atoms produce specific colours when heated or excited and helped create the field of quantum mechanics. Although later discoveries showed that electrons do not move in fixed orbits as Bohr described, his model remains one of the most important steps in understanding atomic structure. The study of the atom also revealed the enormous power hidden inside it. In the early 20th century, Albert Einstein's famous equation E equals mc squared showed that mass and energy are interchangeable. This meant that even a tiny amount of mass contains a tremendous amount of energy. Later, scientists learned how to release this energy by splitting atomic nuclei, a process known as nuclear fission. This discovery led to both nuclear power and nuclear weapons. On the other hand, nuclear fusion, which combines atomic nuclei instead of splitting them, is the process that powers the sun and all the stars. Fusion releases even more energy than fission, and is the ultimate dream of clean energy for humanity. Yet, despite all our scientific advances, the atom remains full of mysteries. For instance, if most of the atom is empty space, why does matter feel solid? The answer lies in the electromagnetic forces between atoms. When you touch an object, the atoms in your hand never actually make contact with the atoms of that object. Instead, the negatively charged electrons on the surfaces repel each other with such strength that it feels solid to us. In reality, what we experience as solidity is the result of invisible forces at work at the atomic level. Atoms are constantly in motion. The electrons spin around the nucleus at incredible speeds, and the atoms themselves vibrate, rotate, and move in space. Even in a solid object like a rock, the atoms are not still. They're constantly vibrating in place. The temperature of a substance is a measure of how fast its atoms and molecules are moving. When we heat something, we're increasing the energy of its atoms, making them move faster. When we cool it, the atoms slow down. At absolute zero, the lowest temperature possible, around minus 273 degrees Celsius, the atoms stop almost completely. When atoms combine, they form molecules, which are the building blocks of all substances. A molecule of water, for example, is made of 2 hydrogen atoms and 1 oxygen atom. The way atoms bond together determines the properties of the material they form. Some atoms share electrons, forming covalent bonds, while others transfer electrons, creating ionic bonds. Metallic bonds, on the other hand, involve a sea of shared electrons that allow metals to conduct electricity and heat. Every material we know, from diamond to salt to steel, owes its characteristics to the way its atoms are arranged and bonded. The number of protons in an atom's nucleus is called its atomic number, and it determines the element's identity. The number of neutrons can vary, creating versions of the same element known as isotopes. For example, ordinary oxygen has 8 protons and 8 neutrons, but there are also heavier forms of oxygen with 9 or 10 neutrons. These isotopes behave chemically like oxygen, but differ in mass and sometimes stability. Some isotopes are stable, while others are radioactive, meaning they spontaneously release energy and particles as they transform into other elements. Radioactive isotopes have many uses, from medical imaging to determining the age of ancient fossils and rocks. The study of atoms has also revealed a deeper unity in the universe. All matter, from the smallest grain of dust to the largest galaxy, is made of the same kinds of atoms. The carbon in your body, the oxygen you breathe, and the iron in your blood were all formed inside ancient stars that lived and died billions of years ago. When those stars exploded as supernovae, they scattered their atoms into space, where they eventually came together to form new stars, planets, and living beings. In a very real sense, every atom in your body was once part of a star. This cosmic connection shows that the story of the atom is also the story of the universe itself. Scientists continue to study the atom with ever-increasing precision, using powerful tools like particle accelerators and electron microscopes. These instruments allow us to see and manipulate matter at the atomic level. In recent decades, the field of nanotechnology has emerged, where scientists and engineers work with individual atoms and molecules to create new materials and devices. This technology is already being used to make stronger materials, faster electronics, and advanced medical treatments. By mastering the atom, humanity has gained the ability to reshape the world at its most fundamental level. Even though atoms are incredibly small, their number in any object is astonishing. A single drop of water contains more atoms than there are stars in the observable universe. Each atom in that drop follows the same physical laws as the atoms in distant galaxies. This uniformity of atomic behavior across the cosmos is one of the most remarkable facts in science. It means that the chemistry of life on Earth could, in theory, occur elsewhere in the universe under the right conditions. The simplicity and beauty of the atom's structure continue to inspire awe. At its core, it is made of just 3 main particles, yet their interactions give rise to everything we know: light, colour, sound, life, and thought itself. The proton defines identity, the neutron adds stability, and the electron governs behaviour. Together, they form a perfect balance that allows the universe to exist in the form we know it. Let us take a closer look at the example of oxygen mentioned earlier. A single oxygen atom is the smallest possible unit of oxygen that still behaves as oxygen. It has 8 protons, 8 neutrons, and 8 electrons. The protons and neutrons form the dense nucleus at the centre, while the electrons occupy 2 shells around it, the first shell holding 2 electrons and the second shell holding 6. Because the second shell can hold 8 electrons, oxygen seeks 2 more by forming bonds. This is why oxygen easily combines with hydrogen to form water, or with carbon to form carbon dioxide. The simple need of an oxygen atom to fill its outer shell is what makes life possible, for without it, there would be no air to breathe, no water to drink, and no plants to grow. The discovery of atoms and their structure has not only changed our understanding of nature, but has also led to countless technological advances. Electronics, computers, lasers, and medical imaging all depend on our knowledge of how atoms and electrons behave. Even the light that illuminates your home comes from the movement of electrons between energy levels in atoms. When an electron jumps from a higher energy level to a lower one, it releases energy in the form of light. This same principle operates in neon signs, television screens, and even the sun itself. The deeper we explore the atomic world, the more we realize that it blurs the boundary between matter and energy. According to quantum mechanics, particles can act like waves, and waves can act like particles. The position of an electron cannot be known with perfect certainty. Instead, we can only describe the probability of finding it in a certain region. This uncertainty is not due to limitations in our instruments. It is a fundamental feature of nature. The atomic world operates on rules that defy classical logic but perfectly explain how the universe behaves at its most basic level. Atoms can also combine in incredible patterns to create crystals, metals, and living cells. The arrangement of atoms determines the structure and properties of a material. In a diamond, for example, each carbon atom bonds with 4 others in a rigid 3-dimensional network, making it one of the hardest substances known. In graphite, however, the same carbon atoms form flat layers that slide over one another easily, making it soft and suitable for use in pencils. This difference arises purely from the way the atoms are arranged, not from the atoms themselves. The same element can take many forms, known as allotropes, depending on how its atoms bond. Throughout human history, the study of atoms has brought us closer to understanding existence itself. It has shown us that everything, from the lightest gas to the heaviest metal, from the tiniest insect to the largest planet, is built from the same basic components. The diversity of nature arises not from the materials themselves, but from the countless ways they can combine and interact. The atomic level, therefore, is not just a scientific concept, it is the hidden architecture of all reality. At the atomic level, everything is both incredibly small and unimaginably vast. The same forces that hold the nucleus together also govern the stars. The same particles that form a drop of water also make up the galaxies. By studying the atom, we have learned that the universe is not made of separate things, but of one continuous fabric woven from the same threads of matter and energy. Every atom carries within it the memory of creation, the echo of the Big Bang and the potential for life. The atom, though invisible to the naked eye, is the most profound symbol of existence, a tiny universe within the universe itself. The molecular level takes us into a fascinating realm where matter begins to take on more recognizable forms, where atoms, those tiny building blocks of the universe, come together to create something greater than themselves. A molecule is born when two or more atoms bond chemically, forming a stable structure that can exist independently. It is at this level that the invisible dance of atoms gives rise to everything around us, from the air we breathe to the cells that make up our bodies. Each molecule, no matter how simple or complex, carries within it a unique arrangement of atoms that determines its shape, behavior, and the role it plays in the vast web of nature. When we say that a molecule is formed by atoms bonding together, we are describing one of the most fundamental acts of creation in the physical world. Atoms are like small units seeking stability, and to achieve that they often share or exchange electrons with other atoms. This sharing or exchange creates chemical bonds that hold the atoms together tightly, forming molecules that can last for mere fractions of a second or for millions of years. Without these bonds and the structures they create, there would be no water, no oxygen, no life, and not even the air we breathe or the materials we touch every day. A molecule can be made up of atoms of the same element or of different elements. When two or more atoms of the same element join together, the resulting molecule is called a simple molecule. Oxygen, for example, exists in nature not as single atoms floating freely, but as pairs of atoms bonded together to form oxygen molecules. Each oxygen molecule, represented by the symbol O2, contains two oxygen atoms sharing electrons in a strong covalent bond. This bond allows the molecule to remain stable and to play its crucial role in supporting life through respiration and combustion. Similarly, nitrogen, another essential gas in our atmosphere, exists as nitrogen molecules, each made of two nitrogen atoms held together by one of the strongest chemical bonds known to science, a triple bond. However, when atoms of different elements bond together, they create something new and often more complex. These molecules of combined elements are called compounds. A perfect example is the water molecule, which is formed when two hydrogen atoms bond with one oxygen atom. Each hydrogen atom shares an electron with the oxygen atom, forming two covalent bonds that create the familiar chemical formula H2O. The result is a molecule that is essential for all known forms of life. What makes water so extraordinary is not only its simplicity, but also the special properties that arise from the way its atoms are arranged. In a single water molecule, the oxygen atom attracts the shared electrons more strongly than the hydrogen atoms do, making one side of the molecule slightly negative and the other slightly positive. This uneven distribution of electrical charge makes water a polar molecule. Because of this polarity, water molecules can attract each other through weak electrical forces called hydrogen bonds. These interactions between water molecules are what give water its unique abilities to dissolve many substances, to remain liquid over a wide range of temperatures, and to regulate heat effectively. These properties are what make water not just common but vital to life itself. Every molecule, whether simple or complex, owes its identity to the specific arrangement of atoms and the types of chemical bonds that hold them together. Chemical bonds act as the invisible glue of the molecular world. They come in several types, but the most important ones are covalent bonds, ionic bonds, and metallic bonds. Covalent bonds, which involve atoms sharing electrons, are particularly common in molecules that form the basis of organic and biological systems. They create stable and flexible structures that can store and transfer energy efficiently. For instance, the molecules that make up sugars, proteins, and DNA, all of which are essential to life, depend heavily on covalent bonding. These molecules can contain dozens, hundreds, or even thousands of atoms, arranged in complex patterns that determine their shape and behavior. In living organisms, the way these molecules interact and combine gives rise to the processes we recognize as life: metabolism, growth, reproduction, and thought itself. Molecules are not static. They are in constant motion, vibrating, rotating, and colliding with one another. In gases, the molecules move freely and rapidly, bouncing off each other and the walls of their containers. In liquids, they move more slowly and stay closer together, sliding past one another while maintaining some degree of attraction. In solids, the molecules are held tightly in fixed positions, vibrating but not moving freely. the state of matter, whether solid, liquid, or gas, depends on the strength of the bonds between molecules and the amount of energy they possess. When we look at the vast diversity of matter in the universe, from the delicate fragrance of a flower to the hard structure of a diamond, we are really seeing the different ways atoms have bonded to form molecules. Carbon, for example, is a remarkable element that can form countless molecular structures. In graphite, carbon atoms link in flat sheets that slide easily over one another, making it soft and ideal for use in pencils. In diamond, the same carbon atoms are bonded differently, creating a rigid three-dimensional network that makes diamond the hardest natural substance known. The difference between graphite and diamond lies entirely in the arrangement of carbon atoms and the type of bonds between them, a striking demonstration of how molecular structure shapes reality. In the molecular world, even the tiniest changes in atomic arrangement can completely alter a substance's properties. The molecules of ozone, O3 for example, consist of 3 oxygen atoms bonded together. This molecule behaves very differently from the oxygen molecules, O2, that we breathe. While O2 supports life, O3 in large amounts can be harmful to living organisms, yet high in the atmosphere, ozone performs an essential function. It absorbs harmful ultraviolet radiation from the sun, protecting life on Earth. This shows how delicate and powerful the molecular balance of nature truly is. The process of forming molecules is guided by the laws of chemistry and physics. Atoms combine in predictable ratios, forming molecules that obey specific rules. These rules are rooted in the arrangement of electrons around each atom. The electrons in the outermost shell, known as valence electrons, determine how an atom interacts with others. Atoms strive to achieve a stable configuration, often by filling their outer shells with a certain number of electrons. This drive for stability is what causes atoms to bond. When atoms share electrons equally, the resulting covalent bonds produce non-polar molecules, like those of nitrogen or hydrogen gas. When electrons are shared unequally, as in the case of water, the molecule becomes polar, leading to the interesting interactions between its molecules. In some cases, one atom gives up one or more electrons entirely to another atom, forming ions that attract each other through electrostatic forces. This kind of attraction creates ionic bonds, as seen in table salt or sodium chloride. Each molecule of salt forms from the combination of a sodium atom, which donates one electron, and a chlorine atom, which accepts it. The resulting ions, positively charged sodium and negatively charged chloride, are held together by strong ionic forces, forming a crystalline solid. Molecules also have different shapes, and these shapes play a crucial role in determining how they behave. The shape of a molecule is influenced by how its atoms are arranged and how the bonds between them are angled. Some molecules are linear, like carbon dioxide, CO2, where the atoms align in a straight line. Others, like water, are bent or V-shaped due to the repulsion between electron pairs around the oxygen atom. More complex molecules, like methane, CH4, take on tetrahedral shapes, where atoms are arranged around a central atom like points of a pyramid. These shapes affect how molecules fit together, react with others, and carry out specific functions in living systems. In biology, the shapes of molecules are particularly important. Proteins, for example, are made up of long chains of amino acids that fold into precise three-dimensional structures. The shape of each protein determines its job, whether it will act as an enzyme speeding up chemical reactions, a structural component of cells, or a messenger carrying signals through the body. Even small changes in the shape of a protein molecule can cause diseases or alter biological functions. DNA, the molecule that carries genetic information, is another perfect example of molecular structure in action. Its famous double helix shape allows it to store and replicate the instructions for life with extraordinary precision. In the non-living world, molecules determine the characteristics of substances just as profoundly. The hardness of a mineral, the transparency of glass, the elasticity of rubber, or the taste of food all depend on molecular composition and structure. For instance, sugar and alcohol are both made of carbon, hydrogen, and oxygen, yet they taste and behave very differently because their atoms are arranged differently. Even something as simple as temperature can affect molecular motion. Heating a substance gives its molecules more energy, causing them to move faster and possibly change state, from solid to liquid or from liquid to gas. Cooling, on the other hand, slows molecular movement and can cause gases to condense or liquids to freeze. At the molecular level, Everything that happens in chemistry and biology, every reaction, every process of life, comes down to how molecules interact with one another. Chemical reactions occur when molecules break apart and their atoms rearrange to form new molecules. This is the essence of change in the physical world. When wood burns, for example, the molecules in the wood react with oxygen molecules in the air. The chemical bonds break and reform, releasing energy in the form of heat and light. The products, carbon dioxide, water vapor, and ash, are all new molecules created by the rearrangement of atoms. The same principle applies to the processes of life. In our bodies, molecules of glucose combine with oxygen molecules during respiration to release energy. This energy powers everything from muscle movement to brain activity. Photosynthesis, the process by which plants create their own food, works in the opposite way. Plants use sunlight to combine carbon dioxide and water molecules into glucose and oxygen. In both cases, molecular bonds are broken and formed in a precise, energy-driven cycle that sustains life on Earth. Molecules are also responsible for carrying signals and storing information. Hormones, neurotransmitters, and DNA all operate on a molecular level. Hormones are molecules that travel through the bloodstream to deliver messages from one part of the body to another, triggering growth, metabolism, or emotional responses. Neurotransmitters are tiny molecules that transmit signals between nerve cells, allowing us to think, feel, and move. DNA molecules, composed of long chains of nucleotides, hold the instructions that guide the development and functioning of every organism. In modern science, understanding the molecular level has opened new frontiers in technology and medicine. Scientists can now design molecules to perform specific tasks, such as killing harmful bacteria, delivering drugs directly to diseased cells, or storing massive amounts of data in molecular structures. Molecular biology, chemistry, and nanotechnology are fields that build upon this knowledge, allowing humanity to manipulate matter on a scale once thought impossible. For instance, in medicine, molecular science helps researchers create drugs that fit precisely into the molecules of the human body, much like a key fits into a lock. These drugs can block or enhance the activity of certain molecules, helping to treat diseases at their source. In materials science, molecular engineering enables the creation of new substances with remarkable properties, such as plastics stronger than steel or fabrics that repel water and dirt. Even in energy production, molecular-level research is leading to cleaner fuels, better batteries, and more efficient solar panels. The study of molecules also reveals the deep unity of nature. Whether it is a molecule of water on Earth, a molecule of methane on Mars, or a molecule of carbon dioxide in the atmosphere of a distant planet, the same laws of chemistry apply everywhere. The patterns of bonding, the types of forces, and the behavior of molecules are universal. This means that by studying molecules here on Earth, scientists can also understand the chemistry of the stars and the potential for life beyond our planet. In the vastness of the universe, molecules are the quiet architects of complexity. From the cold clouds of interstellar space, where molecules form in the dust and gas of newborn stars, to the warm oceans of Earth, where they assemble into living cells, molecular structures are the thread that connects all matter. Astronomers have detected molecules like water, methane, and ammonia in distant regions of space, suggesting that the chemistry of life might not be unique to our world. These cosmic molecules float through the darkness, waiting for the right conditions to combine and perhaps give rise to new worlds and new forms of life. In the laboratory, scientists continue to uncover the secrets of the molecular world. They use advanced tools like electron microscopes and spectrometers to study the shapes, motions, and interactions of molecules. They can even simulate molecular behavior using computers, predicting how new molecules might form or how existing ones might react under different conditions. This growing understanding helps explain not only how matter behaves, but also how life began and how it continues to evolve. Every breath we take, every drop of water, every grain of sand, and every cell in our bodies is made of countless molecules working together in harmony. The molecular level is where chemistry meets life, where the invisible architecture of the universe takes form. It is a world of endless variety and delicate balance, a realm where beauty exists not in what we can see, but in what we can understand. The planetary and stellar levels deal with two closely connected parts of the universe. The planetary level focuses on planets, their moons, and the fascinating systems they form together. It explores how planets move around their stars, how their atmospheres develop, what their surfaces are made of, and even whether they might be able to support life. This level also studies the unique features of each planet, from the blazing deserts of Mercury to the icy plains of Neptune, and from Earth's living oceans to the frozen moons that circle the giant planets. The stellar level, on the other hand, looks deeper into the stars themselves, the great fiery engines that light up the universe. It examines how stars are born from clouds of gas and dust, how they live for millions or even billions of years, and how they eventually die, sometimes in brilliant explosions that scatter new elements across space. These elements then become the building materials for new stars, planets, and even life. Both the planetary and stellar levels are deeply linked, like two parts of a single grand story. Planets form from the leftover material that surrounds young stars, and the life of those planets depends greatly on the behavior of their parent stars. A star's heat, light, and radiation shape the worlds that orbit it, influencing their climates, atmospheres, and potential for life. In turn, the existence of planets and their movements can also affect the stability and evolution of the star system as a whole. The scientific study of planets is one of the most fascinating branches of astronomy and planetary science, involving the exploration of their atmospheres, interiors, and the complex processes through which they form and evolve. Planets are among the most diverse objects in the universe, ranging from the rocky worlds like Earth and Mars to the massive gas giants such as Jupiter and Saturn, and to even more exotic types discovered around distant stars. Understanding planets means understanding the fundamental mechanisms that shaped our own solar system and countless others across the Milky Way galaxy. The field requires an integration of physics, chemistry, geology, and atmospheric science, as it deals with materials, forces, and interactions that span an enormous range of temperatures, pressures, and timescales. The birth of planets begins within a swirling disk of gas and dust that forms around a newly born star. When a molecular cloud collapses under its own gravity, a star ignites at the center, and the leftover material flattens into what scientists call a protoplanetary disk. This disk is primarily composed of hydrogen and helium gas, along with dust grains made of silicates, carbon compounds, and ices. Over time, small solid particles within the disk collide and stick together through electrostatic forces, forming larger and larger aggregates. These aggregates eventually grow into kilometer-sized bodies known as planetesimals. As planetesimals collide and merge, their gravitational pull becomes stronger, allowing them to attract even more material and gradually build up into planetary embryos. The process of planetary formation can take millions of years, depending on the mass and temperature of the disk and the distance from the central star. In the inner regions of the disk, where temperatures are high, volatile compounds like water and methane cannot condense, so rocky planets form primarily from silicate and metal materials. In the outer, colder regions of the disk, ices can accumulate, allowing the formation of much larger planetary cores that can capture vast amounts of gas from the disk before it dissipates. This difference in composition explains why our solar system contains small terrestrial planets close to the Sun and massive gas and ice giants farther away. The study of these processes provides insight into why planetary systems differ so widely in size, structure, and composition. Gravitational interactions between forming planets and the gas in the disk can also lead to dramatic changes in their orbits. Some young planets migrate inward toward their stars, while others move outward or even get ejected entirely. These migrations can shape the final architecture of a planetary system, influencing where planets end up and whether smaller bodies such as asteroids and comets survive. Planetary migration also helps explain why astronomers have found so many exoplanets, planets orbiting other stars that are much larger than Earth yet orbit very close to their parent stars, in regions where gas giants could not have originally formed. As a planet forms and grows, its interior becomes differentiated. The process of planetary differentiation occurs when the planet's materials separate according to their densities. Heavy elements such as iron and nickel sink toward the center, forming a metallic core, while lighter silicate materials rise to form the mantle and crust. This separation is driven by heat produced from the decay of radioactive elements, the energy of accretion, and compression by gravity. The result is a layered structure that affects everything from magnetic field generation to volcanic activity and surface geology. To study planetary interiors, scientists rely on indirect methods because direct observation of a planet's deep layers is impossible. One of the most powerful techniques is seismology, the study of how vibrations or seismic waves travel through a planet. On Earth, seismologists measure waves generated by earthquakes to map the structure of the crust, mantle, and core. These waves travel at different speeds depending on the material they move through, revealing changes in composition and density. On the Moon, instruments left by astronauts during the Apollo missions detected moonquakes that provided insight into its internal layering. Similar techniques can be applied to other planets when landers are equipped with seismometers, as demonstrated by NASA's InSight mission on Mars, which recorded Marsquakes and helped identify the planet's core size and mantle properties. Planetary interiors can also be studied through measurements of gravity and magnetic fields. Variations in a planet's gravitational field reveal differences in internal mass distribution, while magnetic fields provide evidence of liquid conducting layers, such as molten iron cores. For instance, Earth's strong magnetic field arises from the motion of molten iron in its outer core, while Mars, which lost its magnetic field long ago, indicates a solidified or inactive core. These magnetic properties influence how well a planet can shield its atmosphere from solar and cosmic radiation, which in turn affects its ability to sustain surface conditions suitable for life. The study of planetary atmospheres is equally essential, as an atmosphere governs a planet's temperature, weather, and potential habitability. Atmospheric studies involve analysing how radiation from a star passes through and interacts with the gases surrounding a planet. When starlight or thermal radiation travels through an atmosphere, some wavelengths are absorbed by molecules, while others are scattered or emitted. This process, known as radiative transfer, helps scientists determine the composition, temperature, and structure of the atmosphere. By examining the spectra of light, either reflected, emitted, or transmitted, researchers can identify the chemical fingerprints of gases such as carbon dioxide, methane, oxygen, nitrogen, and water vapor. Each molecule absorbs light at specific wavelengths, allowing astronomers to detect them even in the atmospheres of planets many light years away. For example, the presence of methane or water vapor in an exoplanet's atmosphere can indicate chemical processes similar to those on Earth, though they may not necessarily imply biological activity. Temperature variations within an atmosphere give rise to weather patterns and climate. The study of atmospheric dynamics explores how winds, convection, and planetary rotation distribute heat. On Earth, the Sun drives a complex system of winds, storms, and ocean currents. On other planets, these dynamics can be far more extreme. Jupiter, for example, displays powerful jet streams and storms such as the Great Red Spot, a giant vortex that has persisted for centuries. Venus, with its thick carbon dioxide atmosphere and sulfuric acid clouds, experiences a runaway greenhouse effect that makes its surface hotter than that of Mercury despite being farther from the Sun. Mars, on the other hand, has a thin atmosphere mostly composed of carbon dioxide with dust storms that can engulf the entire planet. Atmospheric escape is another important factor in planetary evolution. Planets can lose their atmospheres over time due to solar radiation, stellar winds, or low gravity. Lighter molecules like hydrogen and helium are especially prone to escape into space. Understanding atmospheric loss helps explain why Mars, which once had a thicker atmosphere and possibly surface water, is now cold and dry. It also informs our understanding of how Earth's atmosphere has been maintained over billions of years, despite continuous exposure to solar radiation. The discovery and study of exoplanets has transformed planetary science into a truly cosmic field. The first confirmed detection of an exoplanet orbiting a Sun-like star came in the year 1995, and since then, thousands of exoplanets have been discovered using various methods. One of the most effective techniques is called transit photometry. This method involves observing the light from a star and detecting small periodic dips in brightness that occur when a planet passes, or transits, in front of it. The amount of dimming reveals the planet's size, while the timing of the transits provides its orbital period. When combined with other data, scientists can estimate the planet's density and composition, determining whether it is rocky, gaseous, or icy. Another major method is the radial velocity technique, which measures the subtle wobble of a star caused by the gravitational pull of an orbiting planet. As the star moves slightly toward or away from Earth, its light shifts in wavelength due to the Doppler effect. These shifts can reveal the planet's mass and orbit, allowing astronomers to infer its properties even when the planet itself cannot be seen directly. Together, transit photometry and radial velocity have identified a vast diversity of planetary systems, including hot Jupiters orbiting extremely close to their stars, super-Earths larger than our planet but smaller than Neptune, and mini-Neptunes that blur the line between terrestrial and gaseous worlds. Direct imaging of exoplanets, though difficult, has also become possible with modern telescopes. By blocking the intense glare of the parent star, astronomers can capture faint light reflected or emitted by the planet itself. Such observations provide data on atmospheric composition, temperature, and even cloud structure. Instruments like the James Webb Space Telescope have allowed scientists to analyze the atmospheres of distant worlds in unprecedented detail, detecting molecules like water, carbon dioxide, and methane in some cases. These findings deepen our understanding of how planets form and evolve under different conditions, expanding the known range of planetary types far beyond those found in our own solar system. Studying the overall arrangement and dynamics of planets within a star system, known as system architecture, is fundamental to understanding how stable or chaotic a planetary system can be. The architecture depends on the initial distribution of material in the protoplanetary disk, the timing of planet formation, and the gravitational interactions between planets and smaller bodies. For example, in our solar system, the orbits of the planets are nearly circular and aligned in a flat plane, which contributes to its long-term stability. In contrast, some exoplanetary systems have planets with highly eccentric or inclined orbits, indicating past gravitational encounters or migrations. Resonances between planets can also play a major role in system architecture. Orbital resonances occur when planets exert regular, periodic gravitational influences on each other. This can either stabilize their orbits or lead to long-term instability. For instance, Jupiter and Saturn in our solar system are near a 2 to 5 orbital resonance, which has shaped the distribution of asteroids and influenced the evolution of the outer planets. In some exoplanetary systems, chains of resonant planets reveal how they migrated inward together during formation. Planetary system architecture can also be influenced by external factors such as passing stars, nearby giant planets, or remnants of the protoplanetary disk. These interactions can scatter planets into new orbits, eject them into interstellar space, or cause them to spiral inward toward their stars. Free-floating planets, those that no longer orbit any star, are thought to be common in the galaxy, drifting silently through the darkness after being expelled from their birth systems. In studying planets, scientists often use comparisons between different worlds to reveal underlying physical principles. This approach, known as comparative planetology, allows researchers to understand how variations in mass, distance, composition, and atmosphere lead to different planetary characteristics. For instance, comparing Earth and Venus shows how two planets of similar size and composition can develop drastically different climates due to differences in atmosphere and solar radiation. Comparing the icy moons of Jupiter and Saturn helps identify how internal heating and chemical composition affect geological activity. The study of planets also extends to their interactions with other components of their systems, such as moons, rings, and magnetic fields. Many planets have moons that provide clues to their formation history. Earth's moon likely formed from debris produced by a giant impact, while the moons of Jupiter and Saturn may have formed from leftover material in the same disk that formed their parent planets. Some moons, like Europa and Enceladus, harbour subsurface oceans beneath their icy crusts, sustained by tidal heating from their planet's gravity. These environments may represent some of the most promising places to search for life beyond Earth. Rings are another fascinating feature found around several planets, most notably Saturn. Planetary rings consist of countless particles ranging from tiny dust grains to large boulders, orbiting in a flattened plane around the planet. They can form from the remnants of moons that broke apart due to tidal forces, or from material that never coalesced into a moon. The structure of rings, including the presence of gaps and waves, provides information about gravitational interactions within the system and the physical properties of the ring particles. The magnetic fields of planets, generated by the motion of electrically conducting fluids in their interiors, play a vital role in shielding their atmospheres and surfaces from high-energy radiation. Earth's magnetosphere deflects charged particles from the solar wind, preventing them from stripping away the atmosphere and protecting life on the surface. Jupiter's magnetic field is much stronger, producing intense radiation belts and auroras at its poles. Understanding these magnetic environments not only helps explain the current state of planets, but also their potential habitability. The study of planetary atmospheres, interiors, and formation is also linked to the study of chemistry and thermodynamics under extreme conditions. Deep inside gas giants like Jupiter and Saturn, pressures reach millions of times higher than those at Earth's surface, and temperatures rise to tens of thousands of degrees. Under such conditions, hydrogen may exist in a metallic state, conducting electricity and contributing to the planet's magnetic field. Understanding these states of matter requires both theoretical models and high-pressure experiments in laboratories on Earth. In the case of rocky planets, mineral physics and geochemistry help scientists model how materials behave under high temperatures and pressures. Experiments simulate the melting of silicates and the crystallization of iron to understand core formation and mantle convection. These studies not only explain planetary structure, but also the geological processes that shape planetary surfaces, such as volcanism, tectonics, and impact cratering. Observations from spacecraft and telescopes provide essential data for testing and refining these models. Missions like NASA's Juno, orbiting Jupiter, measure gravitational and magnetic fields to probe the planet's interior, while the European Space Agency's JUICE mission aims to explore the icy moons of Jupiter. The Mars rovers, orbiters, and landers have revealed an extraordinary amount of information about the planet's geology, past climate, and potential for life. The data from these missions complement the study of exoplanets by providing detailed examples of planetary processes within our own solar system. The study of radiation transfer through planetary atmospheres is another area of deep scientific importance. Radiation transfer determines how energy moves through an atmosphere by absorption, emission, and scattering. It governs the balance between incoming stellar energy and outgoing infrared radiation, thereby controlling a planet's temperature. By solving the equations of radiative transfer, scientists can predict temperature profiles, cloud formation, and spectral signatures observable from telescopes. The detection of exoplanet atmospheres using transit spectroscopy relies on measuring tiny differences in starlight as a planet passes in front of its star. During a transit, some of the star's light filters through the planet's atmosphere, leaving behind absorption lines that reveal its chemical makeup. These observations have led to the identification of water vapor, sodium, potassium, and even carbon-bearing molecules in distant worlds. As instruments improve, scientists hope to detect biomarkers, molecules such as oxygen, ozone, or methane that might indicate biological activity. Planetary system architecture, when combined with knowledge of individual planets' compositions and orbits, provides a window into the history of planetary formation. Systems with closely spaced planets may have formed through gentle migration within a calm disk, while systems with highly eccentric orbits may have experienced violent interactions or collisions. The statistical study of thousands of exoplanetary systems reveals patterns that inform our understanding of how common various types of planets are. For example, it appears that small rocky planets similar in size to Earth are quite common throughout the galaxy, while giant planets like Jupiter are less frequent but exert strong influences on their system's dynamics. In studying all these aspects, planet formation, interior structure, atmospheric behavior, and system architecture, scientists are constructing a unified picture of planetary evolution from the earliest stages of star formation to the mature systems we observe today. The data collected from telescopes, spacecraft, and laboratory experiments merge into theoretical models that describe how matter behaves under cosmic conditions, how energy flows through planetary systems, and how stable environments capable of supporting life may arise. The scientific study of planets is, therefore, a complex and evolving discipline that connects many branches of knowledge. Each new discovery of a planet, whether within our solar system or beyond, adds a crucial piece to the vast puzzle of cosmic evolution. The interplay between physics, chemistry, and observation drives the field forward, continually expanding humanity's understanding of the worlds that share our universe. The study of stars is one of the most fascinating and far-reaching branches of astronomy, opening a window into the deep structure of the universe and the very origins of light itself. Stars are the luminous engines that illuminate the cosmos, shaping galaxies, creating planets, and producing the elements that make life possible. Every point of light we see twinkling in the night sky is a distant sun, each with its own story, a story of birth, transformation, and eventual death. The life of a star is an extraordinary journey that can span billions of years, governed by the laws of gravity, nuclear fusion, and cosmic evolution. From the moment a star is born within a cloud of gas and dust to the time it fades into a white dwarf, neutron star, or black hole, it undergoes a remarkable cycle that connects all matter in the universe. Stars begin their existence deep within vast cold regions of space known as molecular clouds or stellar nurseries. These immense clouds are composed mostly of hydrogen gas mixed with helium and traces of heavier elements and cosmic dust. Within these dark and quiet regions, gravity slowly begins to pull matter together, forming denser and denser clumps. Over long periods of time, sometimes stretching across millions of years, these clumps grow more compact and their centers begin to heat up. The process of star formation is delicate and complex, a balance between gravity, which tries to pull matter inward, and pressure, which resists collapse. When gravity becomes strong enough to overcome this pressure, the gas cloud collapses rapidly, forming a protostar, a young, hot, glowing sphere of gas that marks the very beginning of a star's life. Inside this protostar, temperatures and pressures continue to rise until they reach a point where nuclear fusion can begin. This is the key event that transforms a collapsing cloud of gas into a true star. Fusion occurs when hydrogen atoms are squeezed together so tightly that they merge to form helium, releasing enormous amounts of energy in the process. This energy radiates outward, creating the light and heat that we see from Earth. At this moment, the star stabilizes, as the outward pressure from the energy of fusion balances the inward pull of gravity. This stable stage is known as the main sequence, and it represents the longest and most peaceful phase of a star's life. During the main sequence phase, the star shines steadily, converting hydrogen into helium in its core. The duration of this phase depends largely on the star's mass. Massive stars, those many times heavier than our Sun, burn their fuel very quickly, sometimes lasting only a few million years. Smaller stars, on the other hand, like red dwarfs, can live for hundreds of billions of years, slowly burning through their hydrogen reserves. Our own Sun, which has been shining for roughly 4.5 billion years, is about halfway through its main sequence life. It will continue to shine for another 5 billion years before it begins to change into something very different. As the hydrogen in a star's core begins to run out, the balance between gravity and pressure shifts. Without enough fusion energy to counteract gravity, the core starts to contract. The outer layers, however, expand and cool, causing the star to swell into a red giant. This transformation can be both beautiful and violent. The outer layers drift away into space, creating vast, colourful clouds of gas and dust called planetary nebulae, while the core continues to shrink and grow hotter. In stars like the Sun, this process will eventually leave behind a small, dense remnant known as a white dwarf, a glowing ember of what was once a mighty star. For stars much larger than the Sun, the story takes a more dramatic turn. Massive stars fuse heavier and heavier elements in their cores, from helium to carbon, oxygen, silicon, and eventually iron. Iron cannot produce energy through fusion, so when it builds up, the delicate balance inside the star collapses. The result is a spectacular explosion known as a supernova, one of the most powerful events in the universe. In just a few moments, the outer layers of the star are blasted into space, enriching the surrounding cosmos with newly forged elements like gold, silver, and uranium. The core that remains can collapse into an incredibly dense neutron star, or, if massive enough, a black hole, a region of space so dense that not even light can escape its gravity. These cosmic deaths are not merely endings but new beginnings, for the materials expelled by dying stars become the raw ingredients for new stars, planets, and even living beings. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones were all created inside stars long before our solar system existed. This continuous cycle of birth, life, and death among the stars is the foundation of cosmic evolution. Understanding this grand cycle requires studying not only how stars are born and die, but also how they live. The internal structure of a star is a complex system where immense forces are constantly at work. At the center, the core is where nuclear fusion occurs, producing vast amounts of energy. Surrounding the core are different layers that transport this energy outward. In some stars, this happens mainly through radiation, photons slowly moving through the dense gas, while in others, convection currents of hot plasma carry energy more efficiently, much like boiling water in a pot. The outermost layer, known as the stellar atmosphere, plays a key role in determining how a star appears to us. It is here that light escapes into space, carrying with it information about the star's temperature, composition, and motion. Astronomers use a variety of techniques to study these outer layers. By analysing the spectrum of light a star emits, scientists can determine what elements it contains. Each element leaves its own distinctive pattern of lines in the spectrum, allowing astronomers to read a star's composition like a chemical fingerprint. The colour of a star also reveals its temperature. Blue stars are the hottest, while red ones are cooler. Through careful observation and analysis, researchers can uncover the secrets of a star's structure and the processes taking place within it. The study of stellar atmospheres is not only about understanding individual stars, but also about gaining insight into the broader workings of galaxies. The light from stars tells us how they evolve, how they influence their surroundings, and how they interact with the gas and dust between them. For example, the intense radiation from young massive stars can blow away surrounding material, triggering or halting the formation of new stars nearby. In this way, stars shape their environment and help regulate the ongoing cycle of creation in the galaxy. Astronomers also study groups of stars known as stellar populations to learn about the history and structure of galaxies. Stars that form at the same time from the same cloud of gas tend to share similar chemical compositions and ages. By studying these groups, scientists can trace how galaxies have changed over billions of years. For example, older populations of stars tend to contain fewer heavy elements, because they formed before many supernova explosions had enriched the interstellar medium with metals. Younger stars, on the other hand, contain higher concentrations of these elements, showing that they formed from material that had already been processed by previous generations of stars. This gradual build-up of heavy elements, known as metallicity, serves as a cosmic record of galactic evolution. There are also different types of stellar populations depending on where they are found in a galaxy. The stars in the thin disk of a spiral galaxy like our Milky Way tend to be younger and richer in metals, while the stars in the galactic halo and globular clusters are generally much older and poorer in metals. These differences reveal how the galaxy formed and evolved over time. By studying how these populations move and interact, astronomers can map the structure of galaxies and uncover their past. Stellar systems are another important focus in the study of stars. Many stars are not alone but exist in pairs or even larger groups. Binary star systems, where two stars orbit a common center of mass, are extremely common in the universe. These systems provide astronomers with valuable opportunities to measure stellar masses and study gravitational interactions. When two stars in a binary system are close enough, they can exchange material, dramatically altering each other's evolution. In some cases, one star may siphon gas from its companion, leading to bursts of energy, novae, or even triggering a supernova explosion if the white dwarf becomes too massive. These intricate interactions show how the lives of stars can be deeply intertwined. In larger multiple star systems, gravitational interactions become even more complex, and the orbits of surrounding planets can be heavily affected. Planets in such systems may experience unstable or shifting orbits, leading to conditions that can either destroy them or push them into entirely new paths. Studying these systems helps astronomers understand how planets form and survive in such dynamic environments. It also sheds light on the diverse planetary systems observed in our galaxy, many of which are very different from our own solar system. The study of stars goes far beyond just observing points of light in the sky. It involves using the full power of modern science and technology to probe their mysteries. Telescopes equipped with spectrometers, interferometers, and space-based observatories allow astronomers to gather light across all wavelengths, from radio waves to gamma rays. Each part of the spectrum reveals different aspects of a star's nature. Radio observations can trace the cool gas and dust from which stars form. Infrared observations penetrate obscuring clouds to reveal newborn stars, and X-ray and gamma-ray studies uncover the violent deaths of massive stars and the energetic processes surrounding neutron stars and black holes. Together, these observations create a more complete picture of stellar evolution and the forces shaping the cosmos. Even with all this knowledge, the life of a star remains one of the most awe-inspiring phenomena in nature. The energy generated by a single star can illuminate entire planetary systems for billions of years. The Sun, our nearest star, emits about 400 trillion watts of energy every second, sustaining life on Earth and driving the climate, the oceans, and even biological processes. Yet the Sun is only an average star among hundreds of billions in our galaxy. The larger stars, known as hypergiants, can shine millions of times brighter than the Sun and have diameters hundreds of times greater. At the other end of the spectrum, tiny red dwarfs may be only a fraction of the Sun's size, glowing faintly but living for unimaginable lengths of time. The forces inside a star are truly immense. In the core, temperatures can reach tens of millions of degrees, and pressures are so high that atoms are stripped of their electrons, forming a dense plasma. Under these extreme conditions, nuclear fusion becomes possible, transforming matter into energy according to Einstein's famous equation, E mc2. This process is what keeps stars shining and prevents them from collapsing under their own gravity. The delicate balance between gravity pulling inward and pressure pushing outward defines every stage of a star's life. When this balance is disturbed by the exhaustion of fuel or by changes in the star's internal structure, the star evolves into a new phase, often in dramatic fashion. Studying these transformations allows scientists to understand the fundamental laws of physics under extreme conditions that cannot be reproduced on Earth. For example, the cores of massive stars provide insights into nuclear reactions, particle physics, and the behavior of matter at incredibly high densities. Neutron stars, which form after supernova explosions, are particularly fascinating because they contain matter so dense that a teaspoonful would weigh billions of tons. By observing the radiation from such objects, astronomers can test theories of relativity and quantum mechanics, gaining knowledge that extends far beyond astronomy itself. The light from stars also serves as a cosmic messenger, carrying information across the vast reaches of space. Some of the starlight that reaches Earth today began its journey millions or even billions of years ago, long before humans existed. By analysing this light, astronomers can peer back into the distant past and study the early stages of the universe. The oldest stars, found in the halo of the Milky Way and in ancient globular clusters, are relics from the time when the first galaxies were forming. Their compositions tell us about the conditions that existed shortly after the Big Bang and how the first elements were created. As telescopes become more powerful, astronomers continue to discover new and surprising types of stars that challenge existing theories. There are pulsars, rapidly rotating neutron stars that emit beams of radio waves, magnetars, stars with magnetic fields trillions of times stronger than Earth's, and variable stars whose brightness changes over time due to pulsation or eclipses by companion stars. Each discovery adds another layer to our understanding of stellar physics and the diversity of the cosmos. The study of stars also reveals how interconnected everything in the universe is. The same physical laws that govern the fusion reactions inside a distant star also operate within the atoms of our own bodies. The elements that make up the Earth and all living creatures were forged in the hearts of ancient stars that lived and died billions of years ago. In a very real sense, we are made of stardust, the universe's way of knowing itself through life and consciousness. Every star, from the smallest red dwarf to the most massive supergiant, plays a role in this grand cosmic story, contributing to the ongoing cycle of creation and transformation that defines existence itself. Throughout history, humanity's fascination with the stars has driven both wonder and discovery. Ancient civilizations used the stars to navigate the seas, mark the seasons, and create myths about gods and heroes. Over time, the study of stars evolved from simple observation into a precise science grounded in physics and mathematics. The invention of the telescope in the early 17th century opened a new era of exploration, allowing astronomers like Galileo Galilei to see the heavens in unprecedented detail. Centuries later, the development of spectroscopy and astrophysics transformed our understanding of what stars are made of and how they function. Today, space telescopes like Hubble and James Webb continue this journey, probing the depths of the universe to study stars being born in distant galaxies. The vastness of the stellar realm is nearly impossible to comprehend. There are estimated to be more than 200 billion stars in our Milky Way galaxy alone, and countless billions of other galaxies fill the observable universe. Each of these galaxies contains its own stars, nebulae, and systems of planets, making the cosmos a seemingly endless sea of light and motion. Yet, despite their number and diversity, all stars follow the same basic principles. They are born from clouds of gas, they shine by fusing elements in their cores, and they eventually die, returning their material to space. The scale and unity of this process are what makes stellar astronomy such a powerful field of study. The evolution of stars and planets is one of the most fascinating stories written across the universe, a story that connects light, matter, time, and life itself. Every star that shines in the sky is more than just a glowing sphere of gas. It is the heart of a vast and dynamic system. Around it, planets, moons, asteroids, and comets circle in intricate harmony, each shaped by the star's birth, growth, and eventual death. The connection between stars and the planets that orbit them is not merely one of gravity. It is a deep and lifelong relationship that determines how planetary systems are born, how they evolve, and even whether they can host life. The life of a star and the destiny of its planets are tied together from the very beginning, woven into the same cosmic fabric that has existed since the dawn of creation. When a star is born from a collapsing cloud of gas and dust, it brings with it the potential to create worlds. This cloud, often many light years wide, contains hydrogen, helium, and traces of heavier elements, materials that have drifted through space for billions of years. As gravity pulls the cloud inward, it begins to spin faster and flatten into a disk. At the center of this swirling disk, the young star ignites, and around it, the leftover gas and dust form what scientists call an accretion disk. It is here, within this glowing disk, that planets are born. Tiny particles collide and stick together, growing into larger and larger bodies until they become the worlds that will one day orbit their star. This process, though simple in description, is slow and complex in reality. It takes millions of years for small grains of dust to become planet-sized objects. As the young star continues to grow hotter and brighter, its energy begins to influence the disk. The radiation from the star pushes away lighter gases in the inner regions, allowing rocky planets to form closer in, while gas giants form farther away, where the heat is less intense. The balance between light, heat, and gravity determines not only where planets form, but also what kind of planets they become. Some rich in rock and metal, others made mostly of gas and ice. The mass of the star plays an enormous role in shaping this entire process. A massive star burns hotter and brighter, but lives for only a few million years before exploding in a spectacular supernova. Smaller stars, like our Sun, burn more slowly and can live for billions of years, giving their planets much more time to evolve and perhaps even develop life. The energy that a star produces through nuclear fusion determines everything about its system, its temperature, its brightness, and the chemical elements it can create. Within the heart of a star, hydrogen atoms fuse to form helium, releasing tremendous energy in the process. As the star grows older, it may fuse helium into heavier elements like carbon, oxygen, and even iron in the case of massive stars. When these stars die, they scatter their enriched material into space, seeding future generations of stars and planets with the building blocks of life. The carbon in our cells, the oxygen we breathe, and the iron in our blood all came from stars that lived and died long before the Sun was born. In this way, the evolution of stars is directly linked to the formation of planets and to the very existence of life. Every new planetary system begins with the ashes of older stars, recycled by the universe into new forms. As the young star matures, its light and radiation begin to have a profound effect on its surrounding planets. The star's brightness can warm the surfaces of nearby worlds, while its radiation can strip away the atmospheres of planets that orbit too close. The fine balance between a star's warmth and its fury determines whether a planet can hold onto its atmosphere or whether it will be blasted bare by solar winds. This balance is crucial for habitability. A planet too near its star may become a dry, scorched desert, while one too far away may be a frozen wasteland. But in between these extremes lies a narrow region known as the habitable zone, where temperatures are just right for liquid water to exist, a key ingredient for life as we know it. The Earth sits comfortably within this habitable zone around the Sun, but even here, the star's influence is constant and powerful. The solar wind, a stream of charged particles that flows outward from the Sun, interacts with the Earth's magnetic field, creating the beautiful displays of light we know as aurorae. These glowing curtains of colour in the polar skies are a reminder of the Sun's invisible power. Without the Earth's magnetic field to shield us, the solar wind could strip away our atmosphere, making the planet uninhabitable. Mars, which once had a thicker atmosphere, lost much of it when its magnetic field weakened, allowing solar radiation to erode it away. This shows how the behaviour of a star can decide the fate of a planet's environment. Stars are not calm and steady entities. They can flare up violently, releasing bursts of energy that can affect their planets in dramatic ways. These stellar flares and storms can alter atmospheres, disrupt magnetic fields, and even damage the delicate chemistry that supports life. For young stars, such flares are especially frequent, making it difficult for newly formed planets to hold onto their atmospheres. Yet at the same time, this radiation also drives chemical reactions that can create complex molecules, including those that form the basis of life. Thus, the same energy that can destroy life can also help create it. The evolution of a star is also reflected in the evolution of its planets. When a star is young, its planets are still forming, their surfaces molten and unstable, their atmospheres filled with gases like hydrogen and carbon dioxide. Over time, as the star stabilizes, the planets begin to cool. Their surfaces solidify, volcanoes erupt, oceans form, and atmospheres evolve. The composition of a planet's atmosphere depends on many factors: its distance from the star, its size, its gravity, and of course, the star's radiation. For instance, a planet close to a hot, bright star may lose its lighter gases, leaving behind a dense atmosphere rich in carbon dioxide, while a planet farther away may retain hydrogen and helium, becoming more like a gas giant. Even within the same planetary system, the diversity of worlds can be astonishing. Around the Sun, we have small rocky planets like Mercury, Venus, Earth, and Mars, gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. Each planet reflects a different part of the Sun's influence. Venus, for example, lies just a little closer to the Sun than Earth, yet that small difference has made it a world of crushing pressure and scorching heat, where clouds of sulfuric acid drift in a thick, suffocating atmosphere. Mars, a little farther from the Sun, is cold and dry, with a thin atmosphere that cannot hold much warmth. Between these two extremes lies Earth, where the balance between sunlight and distance allows water to flow and life to thrive. The connection between stars and planets does not end when the star reaches middle age. As a star grows older and begins to run out of hydrogen fuel, it changes. For stars like the Sun, this means swelling into a red giant, expanding so much that it may engulf nearby planets. During this stage, the star's outer layers grow cooler and redder, but its radiation increases dramatically, baking and sometimes destroying the inner planets. Outer planets may see their frozen moons thaw, creating temporary oceans or atmospheres. Even as destruction unfolds, new forms of transformation take place. When the star eventually sheds its outer layers and becomes a white dwarf, the remnants of its system may still orbit around it, silent witnesses to billions of years of cosmic history. Massive stars, on the other hand, end their lives in a far more violent way. After burning through their fuel, they explode as supernovae, releasing enough energy to outshine entire galaxies for a brief time. The shock waves from these explosions can trigger the formation of new stars by compressing nearby clouds of gas, beginning the cycle all over again. The heavy elements forged in the dying moments of the star are cast out into space, enriching the interstellar medium and providing the raw materials for future worlds. The iron in our blood, the gold in our jewellery, and the calcium in our bones all came from such explosions. Thus, the life and death of stars are directly responsible for the richness of the material universe. The study of these linked processes, how stars and planets form, evolve, and interact, reveals a deep unity in the cosmos. It shows that planets cannot exist without stars, and stars in turn shape the destinies of their planets in countless ways. The very conditions that make a world habitable are set by its parent star's properties, its size, its temperature, its radiation, and its magnetic activity. The delicate dance between light and gravity, between radiation and matter, creates the environments where planets can either become lifeless stones or living worlds. In recent years, astronomers have discovered thousands of planets beyond our solar system. exoplanets orbiting distant stars. Many of these systems show the same patterns seen in our own: a young star surrounded by a disk of dust, planets forming at different distances, and the effects of stellar radiation shaping their fates. Some of these exoplanets orbit small, cool stars called red dwarfs, which are far more common than stars like the Sun. Although red dwarfs burn dimly and live for trillions of years, they are also known for intense flares that could strip away the atmospheres of nearby planets. Yet their long lifespans might also give life plenty of time to develop, provided a planet can endure the harsh conditions. In some systems, planets orbit so close to their stars that they are tidally locked, with one side always facing the light while the other remains in eternal darkness. The day side burns with heat, while the night side freezes, and only a narrow band between them might be warm enough for liquid water to exist. In others, planets orbit multiple stars, experiencing complex cycles of light and shadow as they move through space. These diverse worlds reveal how deeply the fate of planets is tied to the nature of their stars. The idea of habitability, once thought to apply only to Earth, has expanded as scientists learn more about these distant worlds. Habitability depends on many factors: the right distance from the star, the right atmosphere, the right chemical balance, but above all it depends on the star itself. A quiet, stable star gives its planets a better chance to develop life, while a violent, unstable one may strip away any hope of habitability. The Sun, with its moderate activity and long lifespan, has given Earth billions of years of stability, allowing life to evolve from simple microbes to complex beings capable of studying the very stars that made them. Even now, the Earth continues to feel the Sun's influence every second of every day. Solar flares can disrupt communications, affect satellites, and even cause electrical blackouts on Earth. The planet's magnetic field, constantly battling the solar wind, protects us from the worst effects. But this cosmic interaction never ceases. The shimmering aurorae that dance over the poles are visible signs of this ongoing relationship. They occur when charged particles from the Sun collide with atoms in Earth's upper atmosphere, releasing bursts of light in green, red, and purple hues. These lights are not just beautiful, they are living reminders of the invisible bond between the Earth and its star. The linked evolution of stars and planets shows that nothing in the universe exists in isolation. Every planet, every moon, every comet, and every grain of dust owes its existence to the life cycle of stars. The story begins in the quiet darkness of interstellar clouds, moves through the fiery birth of stars, the slow dance of planetary formation, the long ages of stellar stability, and finally, the explosive or fading end of the star's life. Yet even after a star dies, its influence continues. The material it leaves behind becomes part of new stars and new planets, continuing the endless cycle of creation. In the grand tapestry of the cosmos, stars and planets are partners in a dance that spans billions of years. A star's mass decides how long it will live and what it will create within its core. Its light determines which worlds may grow warm enough to sustain oceans or cold enough to freeze solid. Its magnetic storms shape the skies of its planets, while its death enriches space with the materials for future worlds. Every stage of a star's life, from its birth in a cloud of gas to its final transformation, writes the story of its planets as well. This cosmic connection is one of the most profound truths of science, that life, worlds, and stars are part of a continuous and interconnected process. The warmth that lights a planet's surface, the atoms that build its rocks and oceans, and even the possibility of life itself all come from the same source, the energy and matter of stars. The life cycle of a star is therefore not just the story of light and fusion, but also the story of how entire planetary systems rise, change, and evolve alongside it. The radiation, magnetic fields, and stellar winds that flow outward from a star may seem destructive, but they also shape the environments that make life possible. They sculpt atmospheres, drive climates, and create the chemistry of life. Even the harshest flares can spark reactions that lead to organic molecules, as lightning on early Earth once did. The balance between destruction and creation, between fire and light, lies at the heart of this linked evolution. Throughout the vastness of space, countless stars are living out their own stories, each surrounded by worlds waiting to be discovered. Some stars are young and wild, still wrapped in the dusty clouds that gave them birth. Others are ancient and dim, their planets frozen and silent, yet all are bound by the same laws of nature, the same cycle of birth, life, and transformation. In every case, the fate of the planets depends on the star that warms them, just as the star's destiny is written in the matter that surrounds it. Thus, the link between stellar and planetary evolution is more than a scientific fact. It is a reflection of the unity of the universe. Every planet tells the story of its star, and every star carries within it the potential for new worlds. The Sun and Earth are but one example of this eternal relationship, a relationship that has shaped the past, defines the present, and will continue to influence the future of the cosmos. Through this link, stars and planets share a destiny written not in words but in light and time, a destiny that stretches across billions of years and countless systems scattered through the endless night of space. The term galactic level can have different meanings depending on where it is used, but all of them share a sense of something vast and extraordinary. In the world of science fiction, for example, the phrase might describe a danger or event so immense that it affects an entire galaxy, like a cosmic war spreading across countless star systems, or a mysterious force threatening billions of worlds. In video games, it can be used to show a high stage of progress, power, or difficulty, suggesting that the player has reached a level where their abilities or challenges extend beyond ordinary limits into the grand scale of galaxies themselves. However, in the field of astrophysics, the phrase takes on a more scientific meaning. Here, galactic level refers to anything that happens across the size or structure of a galaxy. A galaxy is a gigantic collection of stars, gas, dust, planets, and dark matter bound together by gravity, often containing hundreds of billions of stars. So, when scientists talk about galactic-level phenomena, they are describing processes or features that stretch across these enormous cosmic systems. Examples include the galactic center, which is the densely packed heart of a galaxy where many stars cluster, and where, in the case of our own galaxy, the Milky Way, a supermassive black hole known as Sagittarius A star resides. Another example of galactic-level phenomena is the orbital movement of stars and solar systems within the galaxy. Our own Sun, along with its planets, travels around the Milky Way's center at an incredible speed. It takes roughly 225 million years for the solar system to complete one full orbit around the galactic core, a period often called a galactic year. This means that since the birth of our planet Earth, about 4.5 billion years ago, it has circled the Milky Way's center only about 20 times. On this grand scale, things move at a pace that is almost impossible to imagine. Clouds of gas stretch for thousands of light years, spiral arms slowly twist like cosmic whirlpools, and ancient stars drift in long, graceful orbits that take millions of years to complete. The galactic level reminds us how immense and interconnected the universe truly is, how every shining star we see in the night sky is part of a vast system of motion, gravity, and energy that extends far beyond human comprehension. When we talk about the galactic level, we are entering a realm so vast and mysterious that even our most powerful instruments and deepest imaginations can barely grasp its immensity. This level refers to the enormous distances, intricate motions, and colossal structures that exist within a single galaxy. A galaxy is not just a cluster of stars, it is a magnificent cosmic city, filled with billions upon billions of suns, countless planets, swirling clouds of dust and gas, dark matter that cannot be seen, and radiant energy that travels across unimaginable distances. To think about a galaxy is to imagine a world beyond human scale, where distances are measured not in kilometers or miles but in light years, and where time stretches across hundreds of millions of years. Within a galaxy, there are many fascinating features, each playing a role in the grand cosmic design. The galactic center, for instance, is often the beating heart of a galaxy, where enormous forces come together. In our own Milky Way, this central region hides a supermassive black hole known as Sagittarius A, a monster with a mass equal to about 4 million suns. Around this black hole, stars whirl in dizzying orbits, pulled by its immense gravity, while clouds of gas spiral inward, glowing with energy as they heat up and emit radiation. The galactic center is one of the most active and extreme environments known to science, filled with powerful magnetic fields, bursts of X-rays, and immense gravitational distortions that bend light and time itself. Beyond the center, a galaxy stretches outward into a grand spiral, elliptical or irregular form depending on its type. The Milky Way, our home galaxy, is a majestic barred spiral with long, graceful arms curving outward like the arms of a cosmic whirlpool. These arms are where most of the galaxy's stars and planetary systems are born, in dense clouds of gas and dust called nebulae. Within these nebulae, the delicate dance of gravity and pressure slowly pulls material together until stars ignite in nuclear fire, shining for billions of years. Between the arms, vast regions of nearly empty space extend, dotted by isolated stars and invisible clouds of gas that drift silently through the galactic plane. One of the most fascinating things about galaxies is that they are constantly in motion. Nothing within them is ever truly still. Every star, every planet, every cloud of dust and gas is in perpetual motion, orbiting the galactic center in a dance that lasts millions of years. Our own sun, for example, is not fixed in one place. It moves in a giant orbit around the center of the Milky Way. It travels at an astonishing speed of about 220 kilometers per second. Yet even at that incredible pace, it takes roughly 225 million years to make a single orbit around the galaxy. This immense duration is what astronomers call a galactic year. To understand how vast that is, imagine this. When the Sun last completed one full orbit around the galaxy, Earth was very different. The dinosaurs were just beginning to roam the land, the continents were joined together in the supercontinent known as Pangaea, and the world's climate was unlike anything we know today. Since then, life has evolved, continents have drifted apart, species have risen and gone extinct, and humanity itself has come into existence, all during just one galactic year. Every time the Sun completes one orbit, the entire history of complex life on Earth could unfold and end again. This gives us a sense of how immense and slow-moving the structures of the galaxy truly are. The stars that accompany the Sun in its orbit also follow their own unique paths. Some move closer to the galactic center, some farther out. The stars in the inner regions of the galaxy complete their orbits more quickly because they are pulled more strongly by gravity, while those on the outskirts move more slowly. This difference in speed, known as differential rotation, causes the spiral arms of the Milky Way to appear stretched and curved, like the flowing arms of a whirlpool. Yet the spiral arms are not solid structures. They are patterns created by waves of density moving through the galactic disk. As these waves pass through, they compress gas and dust, triggering the formation of new stars, which light up the arms and make them glow. The galactic disk, where most stars are found, is relatively thin compared to the overall size of the galaxy. It extends for more than 100,000 light-years across, but is only about 1,000 light-years thick. Above and below this disk lies the galactic halo, a vast, faintly glowing region that surrounds the entire galaxy like a ghostly sphere. The halo contains old stars, ancient star clusters known as globular clusters, and the mysterious substance called dark matter. Scientists believe that dark matter makes up most of the galaxy's mass, yet it cannot be seen directly. It does not emit or absorb light, but its gravitational influence is felt everywhere, holding the galaxy together and preventing it from flying apart as it spins. Within the galactic environment, there are countless smaller structures, star clusters, nebulae, supernova remnants, and molecular clouds that each tell a story of creation, destruction, and renewal. When massive stars reach the end of their lives, they explode as supernova, scattering heavy elements into space. These elements, carbon, oxygen, iron, and many others, become the building blocks of new stars, planets, and eventually life itself. The galaxy is a great recycler, endlessly turning old material into new, ensuring that the atoms that once formed one star might one day form another, or even the life on a distant world. Amidst this grand motion and transformation, energy flows across vast distances in the form of radiation. The galaxy is filled with many types of radiation, ranging from visible light to invisible forms like radio waves, X-rays, and gamma rays. One of the most intriguing forms of radiation is known as galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They originate from sources within our galaxy, such as supernova explosions, pulsars, and the regions surrounding black holes. When these violent events occur, They hurl particles outward with incredible force, filling the galaxy with a constant rain of cosmic radiation. For travelers in space, galactic cosmic rays pose a serious challenge. Unlike the gentle light from stars, these particles can pass through metal and human tissue, damaging spacecraft electronics and posing health risks to astronauts. On Earth, we are shielded from most of this radiation by our planet's magnetic field and thick atmosphere. But once outside Earth's protection, such as in deep space between planets, exposure to cosmic rays becomes a serious concern. Future missions to Mars and beyond will have to find ways to protect astronauts from this invisible but deadly radiation. Scientists study cosmic rays not only for safety, but also to learn more about the galaxy itself. These high-energy particles carry information about the violent processes that created them. By detecting and analysing them, astronomers can learn about supernova explosions, the behaviour of magnetic fields, and even the structure of the galaxy's spiral arms. Some cosmic rays may even come from mysterious sources that have not yet been fully understood, hinting at powerful phenomena still hidden in the depths of the Milky Way. Radiation also plays another important role. It allows us to see the galaxy in all its complexity. When we look up at the night sky, we see only the faint band of light we call the Milky Way. But this is just a small fraction of what our galaxy truly emits. Using telescopes that detect different kinds of radiation, astronomers can observe the Milky Way in radio waves, infrared light, ultraviolet light, X-rays, and gamma rays. Each of these forms of radiation reveals a different part of the galaxy's structure. Radio telescopes, for example, can see the cold gas clouds that form new stars. Infrared telescopes can peer through dust to reveal hidden star-forming regions. X-ray and gamma-ray telescopes can detect the violent emissions from black holes, neutron stars, and supernova remnants. Through these observations, scientists have built a detailed picture of our galaxy. They have mapped the distribution of stars, traced the spiral arms, and measured the motion of gas clouds and star clusters. They have also discovered that the Milky Way is not alone. It is surrounded by smaller companion galaxies, such as the Large and Small Magellanic Clouds, and is part of a larger cosmic family known as the Local Group. Even at the galactic level, there are connections that reach beyond the boundaries of a single galaxy, hinting at the vast web of the universe that ties everything together. But within one galaxy, the distances themselves are so enormous that they challenge the human mind. The nearest star to our Sun, Proxima Centauri, is more than 4 light-years away. That means the light we see from it today began its journey 4 years ago. To travel such a distance using current technology would take tens of thousands of years. And yet, even though this seems vast, Proxima Centauri is practically our next-door neighbour compared to the scale of the Milky Way. The diameter of our galaxy is about 100,000 light-years, meaning that light itself would take 100,000 years to cross from one side to the other. Within that span, there are about 400 billion stars, each with its own system of planets, moons, and possibly life. The idea of movement on this scale is difficult to grasp. Everything in the galaxy is in constant motion. The stars orbit, the gas clouds swirl, and the spiral arms rotate. But from our tiny vantage point on Earth, it all appears still. The patterns of stars we see in the night sky, the constellations that humans have recognized for thousands of years, are actually shifting very slowly as the Sun and its neighboring stars move through space. Over millions of years, the familiar constellations will change shape completely, though the change is too slow to notice in a single lifetime. The Sun's journey around the galaxy is not a simple circle. It moves in a gentle wave-like path, sometimes rising above the galactic plane and then dipping below it again, influenced by the gravitational pull of nearby stars and clouds of gas. The entire solar system travels with it, like a tiny passenger on a vast cosmic voyage. As it moves, the solar system passes through different regions of the galaxy, some more crowded with stars, others more sparse. These journeys may even have subtle effects on Earth's environment over long timescales, as changing cosmic conditions affect the amount of radiation that reaches our planet. Even beyond the visible parts of the galaxy, there are structures that cannot be seen but that shape everything we observe. The dark matter halo, for instance, is believed to extend far beyond the visible stars, perhaps 10 times farther. It acts as an invisible skeleton, holding the galaxy together through gravity. Without dark matter, the outer stars would be moving too fast to stay bound to the galaxy. They would simply fly off into space. But the unseen mass of dark matter keeps them in orbit, maintaining the galaxy's overall shape and stability. Another important feature of the galactic level is the magnetic field. The Milky Way has a vast magnetic field that threads through its disk, influencing the motion of charged particles and shaping the flow of cosmic rays. Though weak compared to the magnetic field of Earth, the galactic magnetic field extends across immense distances and plays a vital role in many processes, from star formation to the confinement of high-energy particles. It interacts with interstellar gas, guiding the flow of charged atoms and affecting how radiation spreads through space. Within the galactic plane, there are also regions of intense activity known as star-forming regions. These are vast nurseries where new stars are born. One of the most famous examples is the Orion Nebula, visible even to the naked eye as a faint patch in the constellation Orion. Inside such regions, gravity causes cold clouds of gas and dust to collapse, forming clusters of young stars surrounded by glowing gas. These newborn stars emit strong radiation and stellar winds that eventually blow away the surrounding material, shaping the nebula into beautiful and intricate forms. As stars age, they continue to shape the galaxy in many ways. When a star like our Sun dies, it sheds its outer layers, forming a planetary nebula and leaving behind a white dwarf, a small dense remnant that slowly cools over billions of years. When much larger stars die, they explode as supernovae, sending shockwaves through space that trigger new waves of star formation. These cycles of birth and death have been happening for billions of years, gradually enriching the galaxy with heavier elements and creating the diversity of stars and planets we see today. The galaxy's history stretches back almost as far as the universe itself. The Milky Way is thought to have formed more than 13 billion years ago, from smaller clouds of gas and early protogalaxies that merged together over time. Even now, the process continues. The Milky Way is slowly absorbing smaller neighbouring galaxies, pulling them in with its gravity and adding their stars to its own. In the distant future, it is expected to collide with the Andromeda Galaxy, another large spiral galaxy nearby. This grand event, though it will not happen for another 4 billion years, will reshape both galaxies, blending their stars and gas into a single, larger system. Every motion, every burst of radiation, and every structure within a galaxy tells part of a vast cosmic story. The galactic level is where stars live their lives, where elements are created and dispersed, where planets form and sometimes harbour life, and where enormous forces shape the destiny of countless worlds. The Milky Way, though just one among trillions of galaxies in the observable universe, is a universe in itself, a boundless domain of stars, dust, radiation, and mystery. At this level, distances are so vast that ordinary human measures lose their meaning. Time itself becomes almost abstract, measured not in years or centuries but in millions and billions of years. Motion becomes a slow, majestic drift, and light, though the fastest thing known, takes thousands upon thousands of years to cross even a small part of the galactic disk. Every particle, every beam of radiation, every orbiting star is part of an immense and interconnected system that has been moving, shining and evolving for almost the entire age of the universe. And within this grand structure, our Sun makes its long journey, carrying with it the planets, moons, and the fragile spark of life on one small world. Each galactic year marks a new chapter in the story of the Milky Way, a story written in light, motion, and time itself. At the intergalactic level, the universe reveals one of its most astonishing and grandest designs, a structure so vast and intricate that it stretches beyond imagination. It is a level where galaxies themselves are not isolated islands of stars drifting alone through the emptiness, but are instead members of an enormous cosmic community. Each galaxy, containing billions or even trillions of stars, becomes a single unit in an even larger system of connections. These galaxies are drawn together by the invisible but powerful force of gravity, which acts like a cosmic thread binding them into clusters, superclusters, and immense filaments that weave the fabric of the cosmos. When one looks at this grand scale, it is clear that galaxies are not scattered randomly through space. Instead, they form an immense network, often compared to a web, known as the cosmic web, a name that captures both its appearance and its vast interconnectedness. This cosmic web is one of the most astonishing discoveries in modern astronomy. It was not visible to the human eye for most of human history, and even when telescopes began to reveal the distant universe, astronomers could only see isolated points of light. But as technology advanced, as radio telescopes, infrared observatories, and space telescopes began mapping the universe in more detail, a breathtaking pattern began to emerge. Galaxies were not evenly spread out like grains of sand on a flat surface. They were organized into immense structures, forming great filaments that stretched for hundreds of millions of light years. Between these filaments were vast, dark voids, enormous empty regions of space that contained almost no galaxies at all. It was as if the universe had spun itself into an enormous, delicate lacework made of galaxies and gas. When we speak of galaxies interacting, we're talking about a process that unfolds over unimaginable stretches of time. Gravity slowly pulls galaxies toward one another, distorting their shapes and stirring their stars and gas into spiraling patterns. These interactions can lead to mergers, where two galaxies combine to form a single, larger one. Sometimes, one galaxy tears another apart, stealing its stars and gas. These cosmic encounters are not violent in the sense of explosions or collisions we know on Earth, because galaxies are mostly empty space. The stars within them are so far apart that they almost never crash into one another. Instead, the encounter is more like a graceful slow-motion dance, where the gravitational pull between galaxies stretches and reshapes them, creating long tidal tails of stars that arc across space. Over time, galaxies gather into clusters, which are the next great structures on this intergalactic scale. A cluster is a family of galaxies bound together by gravity, often containing hundreds or even thousands of member galaxies. These clusters are filled with not only stars and galaxies, but also with extremely hot gas that glows in X-rays, and with large amounts of dark matter, an invisible substance that does not emit or absorb light but whose gravity shapes the cluster's structure. The space between galaxies in a cluster is not empty. It is filled with thin, hot plasma and threaded with magnetic fields. The largest galaxies and clusters often sit near the center, having grown enormous by swallowing smaller neighbors over billions of years. These central giants, often called CD galaxies, can span hundreds of thousands of light years, making them some of the most massive structures in the known universe. Clusters of galaxies themselves do not exist in isolation. They too group together, forming superclusters, vast collections of galaxy clusters linked by gravity and stretched across hundreds of millions of light years. A supercluster is so vast that light, travelling at nearly 300,000 kilometers per second, would take hundreds of millions of years to cross from one side to the other. Our own Milky Way galaxy, along with the Andromeda Galaxy and many smaller galaxies, belongs to a cluster known as the Local Group. This local group in turn is part of a larger supercluster called the Laniakea supercluster, which spans about 520 million light years. Laniakea means immense heaven in Hawaiian, and the name captures perfectly the grandeur of the structure that holds our cosmic neighborhood together. Within Laniakea, thousands of galaxies are linked by gravity, forming streams that flow toward a gravitational center known as the Great Attractor, an unseen region that exerts a mysterious pull on our entire part of the universe. But even superclusters are not the final step in this cosmic hierarchy. They too connect to form even larger patterns, enormous filaments that stretch like tendrils across space, linking superclusters into the vast web that defines the structure of the universe. These filaments can extend for more than 1 billion light years, forming the backbone of the cosmic web. Between the filaments lie the great voids, empty spaces so large that entire clusters of galaxies could fit inside them. The contrast between these luminous threads of galaxies and the dark voids between them creates a cosmic tapestry of astonishing beauty and complexity. It is a pattern that repeats itself at every scale, from the smallest groups of galaxies to the largest cosmic structures known. To imagine the intergalactic level, it helps to picture the universe not as a flat expanse, but as a three-dimensional network. The filaments are like the glowing strands of a spider's web suspended in space, while the voids are like the dark gaps between the threads. The galaxies that we see through telescopes are tiny jewels embedded in these strands, connected to one another across unimaginable distances by the invisible pull of gravity and by the flow of dark matter. The gas within these filaments is thin, far thinner than any vacuum we could create on Earth, yet it stretches for millions of light years, acting as a bridge through which galaxies and clusters exchange material. This gas also glows faintly, heated by shock waves that move through it as the universe evolves. The formation of this grand cosmic network began in the earliest moments after the Big Bang, nearly 14 billion years ago. In the beginning, the universe was almost perfectly uniform, filled with a hot, dense soup of particles. But tiny fluctuations in density, small differences in how matter was distributed, were enough to set the stage for everything that followed. Over time, gravity amplified these small variations, pulling matter together to form denser regions. These regions became the seeds of galaxies, clusters, and filaments. Dark matter, which makes up most of the mass of the universe, played a crucial role in this process. Although invisible, it provided the gravitational scaffolding around which ordinary matter, the matter that makes up stars, planets, and people, could gather and form galaxies. As the universe expanded, these regions of higher density drew in more matter, while the empty regions became emptier. The result was a web-like pattern that grew more pronounced over billions of years. Computer simulations of the universe's evolution show this process vividly. Starting from nearly uniform conditions, tiny ripples in the early universe grow into a vast network of filaments and nodes. The densest nodes are where galaxy clusters form, while the long strands between them contain smaller groups of galaxies and diffuse gas. The voids between the filaments grow larger over time as matter flows out of them, creating the enormous empty regions we see today. Within this web, galaxies do not remain still. They move along the filaments, pulled by gravity toward the dense nodes at their intersections. Over cosmic time, galaxies can travel millions of light years along these invisible highways, falling toward clusters and merging with other galaxies along the way. The flow of matter through the filaments resembles a kind of cosmic circulation system, where galaxies, gas, and dark matter continuously move through the network, feeding the growth of clusters and superclusters. Some astronomers describe this as the universe breathing, an endless cycle of collapse and expansion that gives rise to structure on every scale. The cosmic filaments themselves are not uniform. Some are thick and rich in galaxies, while others are thin and faint. They can twist and curve, intersecting with other filaments at dense nodes where clusters form. The regions where multiple filaments meet are among the most energetic environments in the universe. Here, immense gravitational forces compress gas to high temperatures, generating X-rays and sometimes triggering the formation of new galaxies. These intersection points are also where dark matter is most concentrated, forming massive gravitational wells that shape the motion of galaxies around them. Observing these structures directly is a challenge, because the distances involved are so vast. Astronomers use a combination of techniques to map them. By measuring the positions and redshifts of millions of galaxies, they can create three-dimensional maps of the universe, revealing the filaments and voids that form its skeleton. Surveys such as the Sloan Digital Sky Survey and the Dark Energy Survey have mapped enormous regions of the cosmos, showing filaments stretching across hundreds of millions of light years. Other observations using X-ray and radio telescopes detect the hot gas that fills the filaments, providing further evidence of their structure. The cosmic web is also connected to the mysterious forces that govern the universe's fate. Dark energy, a still unknown force that drives the accelerated expansion of the universe, influences how these structures grow over time. As the universe expands faster and faster, gravity struggles to pull galaxies together, slowing the formation of new clusters and superclusters. In the distant future, this acceleration may cause the cosmic web to stretch so much that galaxies become isolated, unable to see or interact with one another. But for now, the web continues to evolve, with galaxies flowing along its strands and clusters merging at its intersections. At the intergalactic level, every interaction is an act of cosmic evolution. When galaxies merge, they ignite bursts of star formation, creating millions of new stars in their wake. The collisions stir up gas, feed supermassive black holes at their centers, and sometimes trigger powerful jets of radiation that can be seen across the universe. These interactions also transform the shapes of galaxies. Spirals can become ellipticals, and irregular galaxies can be reshaped into new forms. In this way, the structure of the cosmic web not only connects galaxies across space, but also shapes their internal lives, influencing how stars form and how black holes grow. The immense clusters at the intersections of filaments are like cities in the cosmic landscape, bustling with galaxies that interact and evolve together. In these dense environments, galaxies experience frequent encounters that strip away their gas, quench star formation, and transform their appearance. The hot plasma filling the cluster can also affect the galaxies, heating their gas and preventing it from cooling to form new stars. Thus, a galaxy's location within the cosmic web determines much of its fate, whether it remains active and full of young bright stars or becomes a quiet red galaxy where star formation has ceased. The voids between filaments, though seemingly empty, are just as fascinating. They are vast regions where the density of matter is far lower than average, sometimes containing only a few lonely galaxies scattered across hundreds of millions of light years. In these cosmic deserts, galaxies evolve in relative isolation, untouched by the gravitational chaos of clusters. Their slow, peaceful evolution provides a contrast to the violent merging and interaction seen in denser regions. Studying void galaxies helps astronomers understand how environment influences galactic evolution, offering clues about the delicate balance between isolation and interaction in the universe. Intergalactic space itself is not completely empty. It contains a thin mist of hydrogen and helium gas left over from the early universe, as well as heavier elements expelled by galaxies through supernova explosions and galactic winds. This intergalactic medium forms a kind of connective tissue between galaxies, carrying information about how the universe has changed over time. When light from distant quasars, the brilliant cores of young galaxies powered by supermassive black holes, passes through this gas, it leaves behind faint absorption lines that astronomers can study. These absorption patterns, known as the Lyman alpha forest, provide a detailed map of the intergalactic medium, revealing the distribution of matter on the larger scales. The story of the intergalactic level is also a story of time. The structures we see today have taken billions of years to form, growing gradually as the universe expanded and cooled. In the earliest epochs, when the universe was only a few 100 million years old, the first galaxies began to form in the densest regions of the cosmic web. Over time, these galaxies merged and clustered together, building the filaments and nodes we observe today. Even now, the process continues. Galaxies still move, merge, and evolve, and the web slowly changes its shape. In this sense, the universe is a living structure, constantly reshaping itself under the influence of gravity, dark matter, and dark energy. If we could look at the universe from far above, beyond the limits of any telescope, the view would be breathtaking. We would see billions of galaxies arranged in intricate patterns, connected by luminous threads of light. Clusters would appear as bright knots where many threads meet, while enormous dark voids would spread between them like vast oceans of nothingness. The Milky Way, our home galaxy, would be just one tiny sparkle along a filament, part of a network that stretches endlessly in all directions. It is a humbling perspective, one that reminds us how small our place in the cosmos truly is. The movement of galaxies within this web is not random. It follows the invisible contours of dark matter, which forms the framework of the cosmic structure. Though dark matter cannot be seen, its presence is revealed by the way it bends light from distant galaxies, a phenomenon known as gravitational lensing. By studying this bending, astronomers can map the distribution of dark matter and trace the hidden skeleton of the cosmic web. What they find is that the visible matter, the stars, gas, and galaxies, makes up only a small fraction of the total structure. The rest is dark matter, shaping the universe from behind the scenes, guiding the motion of galaxies like an unseen hand. As galaxies move along filaments toward clusters, they sometimes collide and merge, releasing bursts of energy that can light up the universe. Some of the most spectacular events occur when entire clusters merge, creating shock waves that ripple through intergalactic space. These colossal mergers can release more energy than anything else in the universe since the Big Bang. They heat gas to millions of degrees, accelerate particles to near the speed of light, and create enormous radio-emitting structures that span millions of light years. Through these processes, energy and matter are redistributed across vast distances, shaping the evolution of the cosmic web itself. Every galaxy within the web carries with it the story of its origins. Some formed early, when the universe was young and dense, while others arose later, in quieter corners of the cosmos. Their stars bear the chemical fingerprints of generations of supernovae, and their shapes tell the story of past mergers and interactions. The galaxies in dense clusters tend to be older and redder, their star formation long quenched, while those in the filaments or near the edges of voids often remain blue and active, still forming stars from cold gas. This variation across the cosmic web adds another layer of complexity to the universe's grand design. The intergalactic level also reveals how small changes in the early universe could lead to the magnificent structures we see today. The tiny fluctuations in density recorded in the cosmic microwave background, the faint afterglow of the Big Bang, eventually grew into the clusters, filaments, and voids that define the universe's architecture. These fluctuations were only one part in 100,000 of the average density. Yet over billions of years, gravity amplified them into vast structures spanning hundreds of millions of light years. In this way, the cosmic web can be seen as the visible imprint of the universe's earliest moments, a fossilized record of its birth and growth. Even now, astronomers continue to discover new details about this immense structure. They find that the filaments are not just bridges of galaxies, but also cosmic highways along which matter, gas, and even magnetic fields flow. They observe that galaxies align themselves along the direction of the filaments, their spins and shapes influenced by the larger cosmic flow. They detect faint emissions from the warm-hot intergalactic medium, gas at temperatures of millions of degrees that fills the space between galaxies, providing new insights into how baryonic matter is distributed across the cosmos. Every new discovery adds another piece to the puzzle, showing that the universe is even more interconnected than once imagined. The intergalactic level is where the story of the universe's structure unfolds in full. It is a realm where galaxies are not merely stars bound by gravity, but nodes in a vast cosmic network, interacting across unimaginable distances. Gravity shapes their paths, dark matter builds their framework, and time weaves their stories together. The clusters, superclusters, and filaments that fill the cosmos are not static or isolated. They are alive with motion, energy, and transformation, extending the universe's grand architecture into infinity. Across the boundless ocean of the cosmos, there exist unimaginable stretches of emptiness and enormous gatherings of matter that weave together the grand architecture of the universe. These vast voids and massive structures extend across distances so great that even light, the fastest thing known to exist, would take millions of years to travel from one side to the other. What we call the large-scale structure of the universe is not a random scattering of galaxies, but a magnificent cosmic web that stretches for hundreds of millions of light years, made up of both matter and the mysterious unseen forces that guide its shape and motion. Within this immense pattern, galaxies are not isolated islands, but tiny flickers in a vast network, connected by invisible threads of gravity, dark matter, and energy that no human eye can directly perceive. When astronomers look deep into the night sky using their most powerful telescopes, they do not simply see stars and galaxies, they see patterns. These patterns reveal that the universe is structured like a web, with thin filaments of galaxies stretching across unimaginable distances, forming walls, clusters, and knots. Between these filaments lie enormous empty spaces called cosmic voids, regions so empty that they contain almost nothing at all. Just a few stray atoms drifting through billions of cubic light years. These voids are not small, some are hundreds of millions of light years wide, vast hollows that seem to echo with the silence of creation itself. The galaxies and clusters that form the threads of the cosmic web surround these voids like delicate lace, outlining their ghostly boundaries. The idea that such an enormous structure could exist was beyond human imagination for much of history. For centuries, people believed that the stars in the night sky formed a static sphere surrounding Earth. Even after astronomers like Galileo Galilei and Isaac Newton expanded our understanding of space, it was not until the 20th century that humanity began to realize the true scale of the cosmos. When astronomers started to measure the distances to galaxies, they discovered that the universe was not just vast. It was filled with structure on scales larger than anything ever conceived. Galaxies grouped into clusters, clusters grouped into superclusters, and beyond that, filaments and walls spanned the observable universe, separated by enormous cosmic voids. One of the most famous of these colossal formations is known as the Sloan Great Wall, an enormous cosmic structure stretching over 1.5 billion light-years across. Another gigantic formation, called the Hercules Corona Borealis Great Wall, may extend more than 10 billion light-years in length, making it one of the largest known structures in the entire observable universe. These immense gatherings of galaxies and clusters form the bright threads of the cosmic web, and they show how matter in the universe has been shaped by the invisible hand of gravity, and by something even more mysterious. This invisible force comes from what scientists call dark matter and dark energy. These two strange components make up almost everything that exists in the cosmos, yet they cannot be seen or touched. The ordinary matter that makes up stars, planets, and even living beings accounts for only a tiny fraction of the universe's total composition. Most of the rest is hidden in forms that defy direct observation. Dark matter acts as the glue that holds galaxies together and shapes their formation, while dark energy pushes the universe to expand faster and faster, stretching the cosmic web wider with time. Dark matter was first suspected when astronomers noticed something strange about how galaxies moved. When they measured the speeds of stars orbiting around the centers of galaxies, they realized that the stars were moving too fast. If only the visible matter, the stars, gas, and dust, were providing the gravity, the galaxies should have flown apart long ago. Something unseen had to be adding extra mass, creating the gravitational pull needed to hold them together. This mysterious mass was called dark matter, not because it is literally dark, but because it does not emit or reflect light. It is invisible, interacting only through gravity. Though no one has yet seen a single dark matter particle directly, its effects can be measured in how galaxies move, and in how light bends as it passes near large structures, a phenomenon called gravitational lensing. Dark energy, on the other hand, was discovered through an even more surprising observation. In the late 1990s, astronomers studying distant supernovae expected to find that the universe's expansion was slowing down, since gravity should be pulling everything back together. Instead, they found the opposite. The expansion was speeding up. This meant that some unknown energy was counteracting gravity on cosmic scales, pushing galaxies away from each other faster and faster. That force became known as dark energy, and it now seems to make up nearly 70% of the total energy content of the universe. Its exact nature remains one of the greatest mysteries in science. Together, dark matter and dark energy shape the vast cosmic landscape. Dark matter creates the scaffolding, the invisible skeleton, upon which galaxies and clusters form. In the early universe, small fluctuations in the density of dark matter began to grow under the force of gravity, attracting ordinary matter and giving birth to the first galaxies. Over billions of years, these galaxies merged and gathered along enormous filaments of dark matter, forming the intricate web we see today. Dark energy, meanwhile, acts as a cosmic architect that stretches the fabric of space itself, widening the gaps between these filaments and deepening the cosmic voids that lie between them. The balance between these two forces, one that pulls and one that pushes, determines the fate and shape of the entire cosmos. When scientists simulate the universe using supercomputers, they can model how dark matter and dark energy interact over billions of years. These digital universes begin as faint clouds of gas and dark matter, slowly evolving under gravity's influence. As time passes, the matter condenses into knots and filaments, just like the structures observed in real galaxy surveys. The simulations reveal that without dark matter, the universe would look entirely different. Galaxies might never have formed in the first place, because ordinary matter alone does not have enough gravitational pull to create such vast structures. The dark matter provides the invisible backbone, guiding the flow of matter and shaping the large-scale geometry of space. The cosmic voids, though seemingly empty, play an equally important role in this grand structure. These regions, where galaxies are rare and matter is sparse, represent the other side of the cosmic balance. As gravity pulls matter into clusters and filaments, it leaves behind huge empty zones. The voids are not truly empty. They still contain thin traces of hydrogen gas, dark matter, and even faint radiation, but compared to the dense regions of the universe, they are astonishingly barren. Some of these voids, like the Bootes void, are so large that if our entire Milky Way galaxy were placed at their center, it would take hundreds of millions of years for light to reach the nearest galaxies on the edge. These empty expanses give the cosmic web its lace-like appearance, shaping the universe into patterns that resemble soap bubbles or foaming waves frozen in time. Astronomers have developed techniques to study both the clusters and the voids, mapping the universe in 3 dimensions. Using large telescopic surveys, they measure the positions of millions of galaxies, plotting them like stars on a vast cosmic map. These maps reveal that galaxies are not spread evenly, but are concentrated in sheets and filaments surrounding immense hollow regions. The distribution looks almost organic, as if the universe were a living structure with veins of light running through dark space. Each bright spot on the map represents a galaxy containing billions of stars, yet together they form shapes and patterns that can only be seen when viewed from a cosmic perspective. The study of these large-scale patterns gives scientists valuable clues about the history of the cosmos. The early universe, just after the Big Bang, was almost perfectly smooth, with only tiny variations in density. Over billions of years, gravity amplified these variations, allowing matter to collect into denser regions. Dark matter accelerated this process, helping galaxies and clusters to form. Dark energy, in turn, affected how quickly these structures spread apart. By studying the distribution of galaxies and the size of the voids, astronomers can learn about how dark matter and dark energy have influenced the universe over time. One of the most remarkable things about these vast structures is that they continue to evolve. Even now, billions of years after the first galaxies formed, gravity is still pulling clusters together while dark energy stretches the space between them. Some clusters are merging to form even larger superclusters, while others are being pushed apart into greater isolation. This dynamic balance creates a living universe, one that is constantly changing and reshaping itself on unimaginable timescales. In the far future, dark energy may continue to accelerate the expansion so much that galaxies become separated by such great distances that they can no longer be seen from one another. The cosmic web would then stretch thinner and thinner, its filaments fading into darkness as the universe expands beyond the reach of light. But for now, astronomers can still trace the delicate threads of matter and light that connect the universe together, seeing in them a record of cosmic history that spans almost 14 billion years. Every galaxy, every star, and every planet ever born owes its existence to these large-scale forces. The space between the galaxies may seem empty, but it is filled with the subtle influences of dark matter and dark energy, guiding the motion of everything from the smallest atom to the grandest supercluster. When we look up into the night sky, we are seeing only the surface of an immense and intricate design that stretches across the whole of space. Behind every twinkling star lies a web of invisible connections, an ancient structure shaped by forces we are only beginning to understand. The vast voids and massive structures that span millions of light years remind us that the universe is not uniform or simple, but complex and dynamic. It is a masterpiece of contrast, regions of incredible emptiness existing beside regions of almost unimaginable density. Galaxies form cities of stars clustered in luminous chains, while the voids between them are silent and vast, like cosmic deserts stretching without end. Both extremes are essential to the balance of the universe, and both are shaped by the same unseen forces that define everything that exists. The grand design of the cosmos is written not in light, but in gravity and expansion, in the quiet dialogue between matter and energy, visibility and invisibility. The cosmic web is both the skeleton and the heartbeat of the universe, its filaments of light tracing the flow of matter through a sea of darkness. Every point within it, from the smallest galaxy to the largest void, is part of a story billions of years in the making. A story written across space and time by the invisible hand of dark matter and dark energy, shaping the universe into the awe-inspiring structure we observe today. The observable universe, the part of the cosmos that human eyes and instruments can detect, stretches across a distance so enormous that it is almost beyond comprehension. It is a realm that extends for tens of billions of light years in all directions, a vast ocean of space filled with countless galaxies, clusters, and mysterious dark energy and dark matter. When astronomers say that the observable universe contains billions of galaxies, they are describing one of the most mind-expanding facts ever known to humankind. Each of those galaxies is not just a cloud of stars, but a majestic island of light, dust, and gas, holding within it millions or even trillions of stars, countless planets, and perhaps other forms of life that we can only imagine. From the earliest moments of human curiosity, people have looked up at the night sky and seen only a scattering of stars twinkling above, unaware that those tiny points of light were part of something much larger and grander. With time, technology, and thought expanded our understanding. The telescope revealed that those stars were only a small piece of a much greater puzzle. Then came the shocking discovery that our own Milky Way, which seemed to be the entire universe, was only one galaxy among billions of others. When astronomers first grasped this truth in the early 20th century, it transformed human understanding forever. The universe was not a small local neighborhood. It was a boundless and intricate cosmic web that stretched beyond imagination. Each galaxy is a colossal system of stars, planets, nebulae, and mysterious black holes. Some galaxies are small and compact, containing just a few million stars, while others are gigantic spirals and ellipticals holding several trillion stars. The Milky Way, our home galaxy, is thought to contain roughly 400 billion stars, each possibly surrounded by its own system of planets and moons. And yet, compared to the full scale of the universe, our galaxy is merely a single grain of cosmic dust floating in an endless expanse. The idea that there are billions of galaxies scattered across the observable universe means that there could be more stars than all the grains of sand on all the beaches and deserts on Earth combined. When astronomers use the word observable, they mean the portion of the universe that light has had time to reach us from since the beginning of cosmic history. Because light travels at a finite speed, about 300,000 kilometers per second, there is a limit to how far we can see. The light from the farthest galaxies has been traveling toward us for nearly 14 billion years, meaning that when we look deep into space, we're actually looking deep into the past. The light captured by powerful telescopes is like a time machine, showing the universe as it was when it was young and newly formed. Beyond that observable edge lies a vast region we cannot see, perhaps stretching forever, filled with even more galaxies and wonders that remain hidden from view. The structure of the universe on this unimaginable scale is often described as the cosmic web. This web is not made of physical strings but of filaments of galaxies and dark matter, forming a vast interconnected network. Between these threads lie enormous voids, regions of almost empty space spanning hundreds of millions of light years. The galaxies are not spread evenly, but are gathered along these filaments, like beads on invisible threads. When viewed in 3 dimensions, the universe appears as a grand cosmic tapestry, where glowing clusters of galaxies connect through bridges of matter, shaping a pattern that resembles a gigantic web or sponge. This pattern is the result of gravity acting over billions of years, pulling matter together from the nearly uniform soup of the early universe into the intricate cosmic architecture we see today. In the earliest moments after the Big Bang, the universe was an almost uniform sea of energy and particles. Over time, tiny differences in density began to grow under the influence of gravity. Regions slightly denser than others attracted more matter, growing larger and more complex. Gradually, gas clouds condensed into stars and stars gathered into galaxies. These galaxies in turn grouped into clusters and superclusters, eventually forming the web-like structure that defines the universe's large-scale pattern. What we see today, the vast interconnected network of galaxies stretching for billions of light years, is the result of those early ripples magnified over cosmic time. The number of galaxies in the observable universe is truly staggering. Estimates from modern astronomical surveys suggest there may be as many as 2 trillion galaxies within the part of the cosmos we can observe. Many of them are faint and small, visible only through the most powerful telescopes. The Hubble Space Telescope, for instance, once pointed at a tiny, seemingly empty patch of sky for days, and what it revealed was breathtaking. That small dark patch, no bigger than a grain of sand held at arm's length, was filled with thousands of galaxies. Each of those galaxies contained billions of stars. When multiplied across the entire sky, the total number of galaxies becomes almost incomprehensible. Each of these galaxies is unique in shape, color, and life cycle. Some are elegant spiral galaxies, their arms gracefully winding outward like cosmic whirlpools. Others are elliptical, more like glowing spheres of light, often ancient and filled with older stars. There are irregular galaxies too, twisted and deformed by gravitational interactions. The diversity of galaxies across the universe is like the diversity of life on Earth, vast, dynamic, and filled with surprises. Many of these galaxies contain mysterious supermassive black holes at their centers, engines of gravity so powerful that not even light can escape their pull. These black holes, millions or even billions of times more massive than the Sun, play a key role in shaping galaxies and influencing the stars within them. The distances between galaxies are beyond ordinary comprehension. Even the nearest galaxy to our Milky Way, the Andromeda Galaxy, lies about 2.5 million light-years away. This means that the light we see from it today left that galaxy 2.5 million years ago, long before modern humans even appeared on Earth. Andromeda and the Milky Way are slowly moving toward each other and are expected to collide in about 4 billion years, merging to form a new, larger galaxy. Yet even this monumental event will be a local event on the cosmic scale. Between clusters of galaxies lie immense regions of emptiness, so vast that entire galaxies could pass through them without ever encountering another star. When we think of billions of galaxies, each filled with billions of stars, the potential for other worlds and perhaps other forms of life becomes almost inevitable. If even a small fraction of those stars have planets similar to Earth, then there could be countless worlds across the universe where life might exist in some form. Some may have oceans and continents, others may be frozen or scorched. There could be civilizations, ancient and wise, gazing at their own skies and wondering, as we do, if they are alone. The idea that the observable universe contains so many galaxies expands not only our scientific perspective, but also our philosophical imagination. It challenges humanity to understand its place in an almost infinite cosmic sea. The large-scale structure of the universe reveals an extraordinary harmony between order and chaos. Gravity acts as the architect, pulling matter together into galaxies and clusters, while dark energy pushes the fabric of space apart, causing the universe to expand. The balance between these opposing forces shapes everything we see. In regions where matter gathers densely, galaxies form and glow brightly. In other regions, dark energy dominates, stretching space and deepening the cosmic voids. Over billions of years, this cosmic dance has sculpted the universe into the web-like form that scientists map today with sophisticated instruments and simulations. When astronomers map galaxies across vast distances, they do not see a random scatter, but a pattern resembling the filaments of a spider's web or the neural network of a brain. Superclusters of galaxies are connected by cosmic bridges, while between them lie immense empty regions called voids. Some of these voids are so large that if the Milky Way were placed at their centre, it would take hundreds of millions of light-years to reach the nearest galaxy. This pattern suggests that the universe has an underlying order governed by the laws of physics, but expressed through forms that seem almost organic and alive. The universe appears to grow like a living structure, shaped by invisible forces that weave galaxies together across cosmic time. The ingredients that make up this cosmic web are not all visible. In fact, the majority of the universe is made of something we cannot directly see. Scientists estimate that only about 5% of the universe consists of ordinary matter, the kind that makes up stars, planets, and people. The rest is hidden in the form of dark matter and dark energy. Dark matter, which makes up roughly a quarter of the total cosmic content, acts like a gravitational glue, holding galaxies and clusters together. It does not emit light or energy, but its presence can be detected through its gravitational effects. Dark energy, on the other hand, is an even greater mystery. It makes up about 70% of the universe, and is thought to be responsible for the accelerated expansion of space. The existence of dark energy means that the universe is not only vast, but also growing larger every moment, with galaxies drifting farther and farther apart. This expansion of the universe is one of the most astonishing discoveries in modern science. It means that space itself is stretching, carrying galaxies along like dots on the surface of an inflating balloon. The farther away a galaxy is, the faster it appears to move away from us. This relationship, known as the Hubble law, is a cornerstone of cosmology. When astronomers look at distant galaxies, they notice that their light is shifted toward the red end of the spectrum, a phenomenon called redshift, which shows that they are receding from us. The higher the redshift, the farther away the galaxy is, and the older the light we are seeing. Some of the most distant galaxies detected today are so far away that their light has travelled for more than 13 billion years, allowing us to glimpse the universe when it was young and the first galaxies were just forming. These early galaxies were much smaller and less organised than the majestic spirals and ellipticals we see today. They were chaotic, filled with bursts of star formation and frequent collisions. Over billions of years, smaller galaxies merged to form larger ones, and stars forged heavier elements in their cores, enriching the cosmic environment. The materials that make up planets, life, and even human bodies were once created in these ancient stars and spread through space when they exploded as supernovae. In this way, every atom on Earth is connected to the larger story of the cosmos. The universe, in all its vastness, is a single, evolving entity, and we are part of its ongoing creation. To study such immense structures, astronomers use telescopes that capture light across the electromagnetic spectrum, from radio waves to gamma rays. Each type of light reveals a different layer of cosmic history. Radio telescopes can trace the distribution of hydrogen gas, the raw material for stars. Infrared telescopes can peer through dust to reveal hidden galaxies. Optical telescopes like Hubble show the visible light of stars and nebulae, while X-ray observatories detect the high-energy emissions from black holes and galaxy clusters. Together, these observations allow scientists to piece together a detailed picture of the universe and how it has evolved over time. Computer simulations have also become a powerful tool for understanding the cosmic web. Scientists feed the laws of physics into massive supercomputers, starting from conditions similar to those just after the Big Bang. Over simulated billions of years, matter condenses, forms filaments and clusters, reproducing the same web-like patterns that astronomers observe in real data. These simulations suggest that the universe's structure emerges naturally from the simple rules of gravity acting on dark matter. They also show that galaxies are not static but part of a dynamic network, constantly moving, merging and evolving as the cosmic web continues to grow. On the grander scales, the observable universe resembles a colossal foam of interconnected filaments and bubbles. Each filament can span hundreds of millions of light-years and contain thousands of galaxies. The largest structures known, such as the Hercules Corona Borealis Great Wall, extend for billions of light-years. These colossal formations are among the largest known in the cosmos, yet they are just part of the grand network that fills space. Despite their enormous size, even these structures are small compared to the total scale of the universe, which might continue infinitely beyond what we can observe. As telescopes become more powerful, astronomers continue to discover new galaxies and deeper cosmic structures. The James Webb Space Telescope, launched in the early 21st century, has already peered farther into space and time than ever before, revealing galaxies that formed only a few 100 million years after the Big Bang. These ancient galaxies show that the universe was already complex in its earlier stages, with stars and clusters forming faster than scientists once believed. Every new discovery adds another thread to the vast tapestry of the cosmic web, deepening our understanding of how matter and energy have shaped the cosmos. The light from these distant galaxies travels across the universe for billions of years, crossing immense stretches of space and passing through regions filled with gas, dust, and dark matter. Along its journey, the light becomes stretched and dimmed, but it carries with it the story of cosmic evolution. When that ancient light finally reaches Earth and is captured by a telescope, it allows astronomers to reconstruct the history of the universe, from its fiery beginnings to its grand web-like structure today. This process is like reading a book written in starlight, with each galaxy representing a chapter in the unfolding story of creation. The universe is not static but constantly changing. Galaxies collide, stars are born and die, and new elements are forged. On the larger scale, the cosmic web itself slowly evolves, as gravity continues to draw matter together and dark energy drives space to expand. Over trillions of years into the future, galaxies may drift so far apart that distant ones will no longer be visible from one another. The universe may become a dark and quiet place, with isolated islands of stars surrounded by endless voids. Yet even then, the memory of this grand structure will remain written in the cosmic background radiation, the faint glow left over from the birth of the universe, reminding that once, the cosmos was filled with light and energy. Even though the observable universe already contains billions upon billions of galaxies, it is likely only a small fraction of the total. The universe could extend infinitely in all directions, far beyond what our instruments can ever reach. Beyond the horizon of what we can see may lie an even greater expanse, filled with uncountable galaxies, stars, and perhaps universes beyond our own. Some cosmological theories suggest that our universe might be one bubble among many, part of a vast multiverse of infinite worlds. If this is true, then the number of galaxies, stars, and worlds may be beyond any human calculation. To imagine the full scale of the observable universe is to confront the limits of human understanding. If one could travel at the speed of light, it would take tens of billions of years to cross from one end to the other. Yet even at that unimaginable speed, we would only be moving through a small fraction of the total universe. The distances are so vast that they defy any ordinary sense of space and time. Every point of light in the night sky is a message from the past, a reminder of the immense scale and age of the cosmos. Every galaxy, every cluster, every shimmering thread of the cosmic web is part of a single, interconnected whole. The atoms that make up stars and planets were once part of the same cosmic furnace that birthed everything we know. When we gaze into the depths of space, we are not merely looking outward, we are looking backward through time and inward toward our own origins. The observable universe, with its billions of galaxies and endless expanses, is not just a distant realm of stars and light, but a mirror reflecting our own existence within an ever-unfolding cosmic story that stretches far beyond imagination. Cosmology is the grand science that tries to understand everything about the universe, how it began, how it changes, and how it behaves. It seeks to describe not only the galaxies and stars we see, but also the invisible forces and hidden energies that shape all of existence. When cosmologists study the expansion of space, the faint glow left over from the birth of the cosmos known as the cosmic microwave background radiation, and the great universal laws that hold everything together, they are really trying to understand the entire story of reality itself, from its first instant to this very moment. The story begins with what is called the Big Bang, a name given to the earliest known event in cosmic history. This event took place around 13,800,000,000 years ago, when all matter, energy, space, and even time were squeezed into an unimaginably small, dense, and hot point. It was not a conventional explosion that burst into empty space, because space itself did not exist yet. Instead, it was the sudden and continuous expansion of space itself, stretching and growing in all directions, carrying with it everything that would later become galaxies, stars, planets, and eventually life. In those first moments, the universe was a sea of energy and radiation, so hot that atoms could not even form. Everything existed as a storm of subatomic particles colliding and separating at speeds close to that of light. As the universe expanded, it began to cool. Within a few 100,000 years, temperatures dropped enough for electrons to combine with protons and form the first atoms, mostly hydrogen and helium. When this happened, light that had been trapped within the dense fog of early matter was finally able to travel freely through space. That ancient light has continued to travel ever since, filling every corner of the cosmos. Today, we can still detect it as a faint background glow, the cosmic microwave background radiation. It is the oldest light in existence, and by studying it, scientists can see a snapshot of the universe as it was only a few 100,000 years after its birth. This radiation is like a fossil record of the cosmos, a whisper from the past that still carries the temperature fluctuations and energy patterns that would later grow into galaxies and clusters of stars. The expansion of space is not something that happens in one place while leaving others untouched. It occurs everywhere at once. Every distant galaxy is moving away from every other one, not because they are travelling through space, but because the very fabric of space between them is stretching. This was first discovered by the astronomer Edwin Hubble in the early 20th century, when he noticed that the light from distant galaxies was redshifted, meaning its wavelength was stretched toward the red end of the spectrum. This was the first clear evidence that the universe was expanding. Since then, scientists have learned that this expansion is not slowing down as they once thought, but actually speeding up, driven by a mysterious force known as dark energy, which makes up most of the total energy in the universe. The cosmic microwave background radiation also helped confirm this ongoing expansion. Measurements made by satellites such as COBE, UMAP, and Planck have shown that the radiation is almost uniform in all directions, but with tiny variations in temperature and density. These small differences acted like the seeds from which galaxies and clusters of galaxies eventually formed under the pull of gravity. The pattern of this background light allows scientists to estimate the age, shape, and composition of the universe. It shows that the universe is very nearly flat on the larger scales, meaning that its overall geometry follows the rules predicted by Albert Einstein's general theory of relativity, which describes gravity not as a force pulling objects together, but as the warping of space and time by mass and energy. Einstein's theory is one of the great universal laws that operates throughout the cosmos, but it is only one part of the picture. Other universal laws govern how matter and energy behave, such as the laws of thermodynamics, which describe how heat and energy move, and quantum mechanics, which explains the strange and tiny world of subatomic particles. These laws remain the same everywhere and at all times. Whether you're in a distant galaxy billions of light years away or standing on Earth, the speed of light is the same, the strength of gravity follows the same equations, and the behavior of atoms obeys the same principles. These unchanging laws are what make cosmology possible, allowing scientists to use observations from our tiny corner of space to understand the whole universe. As the universe continued to expand over billions of years, its structure grew more complex. Small clumps of matter began to pull together under the force of gravity, forming the first stars and galaxies. These early galaxies merged and interacted, forming immense clusters and cosmic filaments that stretch for millions of light years. Yet through all these grand changes, the cosmic background radiation kept cooling and fading, its temperature now only a few degrees above absolute zero. This faint warmth is a silent reminder of the universe's fiery beginning, and it still fills the sky in every direction, even though our eyes cannot see it. Cosmologists use advanced telescopes, satellites, and mathematical models to study this radiation, as well as the movement of galaxies and the behavior of dark matter and dark energy. By comparing the data to their theories, they can trace how the universe evolved from that first moment to the present day. They can even make predictions about what might happen in the distant future. Some models suggest that the expansion may continue forever, causing galaxies to drift so far apart that the universe becomes dark and cold. Others propose that the universe might eventually slow down and collapse back in on itself in a big crunch, or that it could tear itself apart in a big rip. Each possibility depends on the balance between gravity, dark energy, and the overall density of matter in the cosmos. The idea of space itself expanding can be difficult to grasp, because we are used to thinking of space as a stage where things happen, not as something that can grow and stretch. Yet, in cosmology, space is dynamic. It has a shape, a curvature, and a history. Galaxies are not flying through pre-existing emptiness. Instead, the distance between them increases because the space that connects them grows larger. If we could somehow watch this process from outside the universe, it might look as if everything were moving away from everything else, but there is no center and no edge. Every point in the universe is expanding away from every other point equally, just like raisins moving apart in rising dough. The discovery of the cosmic microwave background radiation in the middle of the 20th century provided one of the strongest proofs for the Big Bang theory. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, detected a faint, persistent noise coming from all directions in the sky. At first, they thought it might be interference or even pigeon droppings in their antenna, but when they cleaned it and the signal remained, they realized they had stumbled upon something extraordinary. The afterglow of creation itself. Their discovery confirmed predictions made by theoretical physicists that such a background radiation should exist, and it earned them the Nobel Prize in Physics. The study of this radiation has become one of the most important parts of modern cosmology. It allows scientists to measure the rate of expansion of the universe, known as the Hubble constant, with increasing precision. It also reveals how matter was distributed in the early universe and helps explain how galaxies and large-scale structures formed. Even the tiniest irregularities in the background radiation have profound consequences, for they show that the universe was not perfectly smooth at the start, and that these tiny imperfections were essential for everything we see today, from stars and planets to human beings. Over billions of years, stars have forged heavier elements in their cores through nuclear fusion, creating the building blocks of life. These stars eventually exploded as supernovae, scattering their elements into space, where they became part of new stars and planets. In this way, the story of cosmology is also the story of us. The atoms that make up our bodies were once part of ancient stars born in the early universe. Every breath we take contains atoms that have travelled across cosmic time, shaped by the same laws that govern the largest galaxies and the tiniest particles. The universal laws that cosmology reveals connect everything, from the birth of the universe to the formation of galaxies, from the behaviour of black holes to the smallest quantum fluctuations. They show that the cosmos is not random or chaotic, but deeply ordered, bound together by mathematics and physical principles that never change. Through these laws, we can understand how light bends around massive objects, how time slows near strong gravitational fields, and how energy transforms from one form to another. These principles are like the language of the universe, written in equations but visible in the stars. Cosmology continues to evolve, driven by new discoveries and more precise measurements. Space telescopes such as the James Webb Space Telescope are now peering back to the first few 100 million years after the Big Bang, observing the earliest galaxies as they began to form. Observatories on Earth are detecting gravitational waves from colliding black holes and neutron stars, offering new ways to test the laws of physics. Every new observation adds another piece to the vast cosmic puzzle, helping humanity understand not only how the universe began, but also how it continues to grow and change. The expansion of space, the faint echo of the cosmic microwave background, and the unchanging universal laws that govern everything together form the framework of modern cosmology. They are the threads that weave the story of the universe, a story that began more than 13 billion years ago and continues to unfold across the endless depths of space and time. At the farthest edges of human thought, beyond the limits of telescopes and even beyond what the most advanced mathematics can confidently describe, lies one of the most daring and mind-expanding ideas ever proposed, the multiverse. It is a vision that stretches reality to its most extreme frontier, suggesting that our universe, vast and ancient as it seems, might be just one small bubble in an infinite sea of other universes. These universes might each be governed by different laws of physics, filled with different kinds of matter, energy, and even dimensions. Some could resemble ours closely, while others might be so strange that our minds can hardly imagine them. The multiverse idea belongs to what can be called the metacosmic level, a realm beyond the known cosmos, where space, time, and the physical constants that shape our reality might not even be the same. At this level, the imagination of science stretches to the outermost edge of possibility. It is here that physicists and cosmologists attempt to answer questions that even the Big Bang cannot fully explain. Why does our universe have the laws it does? Why do the fundamental forces and constants seem so perfectly balanced to allow life to exist? Could it be that this balance is not a unique miracle, but simply one result among countless others in a vast multiverse? The concept of multiple universes is not new in the history of thought. Ancient philosophers once speculated about other worlds beyond our own, scattered across an endless cosmos. However, in modern science, the idea began to take a more serious and mathematical form during the 20th century, when quantum mechanics, relativity, and cosmology started to reveal that reality might be far more flexible and complex than anyone had ever imagined. The 20th century brought theories that shook our understanding of existence, from Albert Einstein's vision of curved space-time to the mysterious and unpredictable world of quantum particles. As physicists struggled to combine these two grand theories into one unified picture, strange possibilities began to appear, and one of them was the multiverse. The first seeds of the modern multiverse idea were planted when scientists realized that the universe might not be infinite in time or space, but that it could have arisen from a single event, the Big Bang, around 13 billion and 800 million years ago. Yet, this discovery also raised deeper questions. If the Big Bang created our universe, what came before it? And could something like it happen again, elsewhere? The equations of cosmology do not forbid such possibilities. In fact, when scientists examined the mathematics behind cosmic inflation, the brief and astonishingly rapid expansion of the universe in its earliest fraction of a second, they found something remarkable. Inflation might not have been a single event that happened once and then stopped. It might be an ongoing process, constantly creating new pocket universes in a vast cosmic foam. This idea is sometimes called eternal inflation. It describes a picture where the fabric of space keeps expanding, with regions occasionally slowing down and forming bubbles, each bubble becoming its own universe, with its own stars, galaxies, and perhaps its own laws of nature. Our universe would then be just one bubble in this immense, constantly growing multiverse. The space between these universes would expand faster than light, separating them forever so that no communication or travel between them could ever occur. The distances are so vast that even light, the fastest thing in existence, could never cross from one to another. In this cosmic landscape, every bubble universe could be different. The strength of gravity might vary. The The speed of light could be slower or faster. Atoms might not even exist in some of them. In some universes, stars could live for only seconds, while in others, they might burn for trillions of years. Some might expand endlessly, while others could collapse into black voids almost immediately. If there are truly countless such universes, then it becomes less surprising that one of them, ours, happens to have the perfect balance of conditions that allow galaxies, planets, and life to exist. In this sense, the multiverse could offer an explanation for one of the great mysteries of existence, why the universe seems so finely tuned for life. The fine-tuning problem has puzzled scientists for decades. The constants of nature, such as the strength of gravity, the mass of the electron, and the energy of empty space, are set with almost impossible precision. If even one of these values was slightly different, the universe might never have formed stars or galaxies, or it might have collapsed instantly after the Big Bang. To some, this seems too unlikely to be random chance. But if there are an infinite number of universes, then every possible combination of physical laws could exist somewhere. We simply happen to live in one of the rare universes where the conditions allow life to emerge. In this view, the multiverse turns the fine-tuning mystery into a statistical certainty. Yet, the multiverse is not just about cosmic inflation. Other branches of physics have stumbled upon similar ideas in completely different ways. Quantum mechanics, the theory that governs the behavior of particles on the smallest scales, also hints at the existence of multiple realities. In the quantum world, particles do not have definite states until they are observed. Instead, they exist in a blend of possibilities. When an observation happens, one of these possibilities becomes real. But what happens to the others? The many worlds interpretation, proposed by physicist Hugh Everett in the mid-20th century, offers a bold answer. All possibilities become real, but in separate branches of the universe. According to this interpretation, every event that could possibly happen does happen, but in different universes. If you flip a coin, in one universe it lands heads, and in another it lands tails. When you make a decision, there might be another version of you in another universe who made a different choice. These universes do not interact or communicate. They simply exist as separate outcomes of the same underlying reality. In this picture, the cosmos is constantly branching, creating new versions of itself with every quantum event. The number of universes could then be unimaginably large, perhaps infinite. While the quantum many-worlds idea and the cosmic inflation multiverse arise from very different areas of physics, they both suggest that reality may not be singular. Instead, existence could be a vast and ever-expanding web of parallel worlds, each with its own timeline and history. Some scientists have even wondered if these different kinds of multiverses might actually be connected. Perhaps the quantum branching happens within each bubble universe, creating even more layers of reality. String theory adds yet another dimension to this vision. Developed in the late 20th century as an attempt to unify all the forces of nature into one framework, string theory suggests that everything in the universe, from the smallest particles to the largest galaxies, is made of tiny vibrating strings of energy. These strings vibrate in multiple dimensions, not just the 3 of space and 1 of time that we experience. According to string theory, the universe might have 10 or even 11 dimensions, most of which are curled up so tightly that we cannot perceive them. But these hidden dimensions could allow for the existence of countless possible universes, each defined by a different way in which the extra dimensions are folded or shaped. This vast collection of possible universes is sometimes called the string landscape. Each configuration could produce different physical laws, different particles, and different values of fundamental constants. The number of possible universes in this landscape is so enormous that some scientists have estimated it to be around 10 to the power of 500, a number far beyond imagination. In this sense, the multiverse is not just a possibility, it might even be a mathematical necessity, emerging naturally from the equations that describe the deepest levels of reality. Closely related to string theory is the idea of brain cosmology, a concept that imagines our universe as a 3-dimensional brain, floating in a higher dimensional space known as the bulk. In this framework, other brains could exist parallel to ours, each one representing a different universe. These universes might be only a microscopic distance away in the higher dimensions, but completely invisible to us because we are confined to our own brain. In some versions of this theory, the collision of brains could even create Big Bang-like events, giving birth to new universes. The entire multiverse in this view could be like a vast ocean of floating membranes, occasionally touching and triggering new creations. The idea of higher dimensional universes also brings fascinating possibilities for the nature of existence itself. If there truly are extra dimensions, they might contain forms of matter or energy that we cannot detect with ordinary instruments. Some scientists have even speculated that dark matter, the mysterious substance that makes up most of the mass in the universe, might be leaking gravity from another brane or universe close to ours. Though still unproven, these ideas attempt to connect the invisible mysteries of cosmology to the hidden architecture of the multiverse. What makes the multiverse concept so extraordinary is not just its boldness, but also its implications. If multiple universes exist, then everything that can possibly happen might already exist somewhere. Every possible history, every possible future, every possible version of reality could be unfolding right now in a different universe. Somewhere, there could be a universe where the laws of physics allow stars made of antimatter, or where time flows backward, or where gravity is repulsive instead of attractive. There could be universes without light, without space, or even without time as we know it. The diversity of these realities would be beyond all human comprehension. However, the challenge with the multiverse is that, at least for now, it remains a largely theoretical idea. Because these other universes would be beyond our observable horizon, we cannot directly see or measure them. Our universe is limited by the speed of light and the finite age of space-time. We can only observe what lies within about 46 billion light-years in any direction. Anything beyond that is forever hidden from view. This makes the multiverse a topic that sits on the border between science and philosophy. It can be described mathematically and may arise naturally from known theories, but it cannot yet be tested with experiments. Still, scientists have tried to find indirect ways of exploring the idea. For example, if another universe ever collided with ours in the distant past, it might have left subtle marks in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Researchers have searched for strange circular patterns or temperature anomalies that could be signs of such collisions. Although no definitive evidence has been found, the search continues, driven by curiosity and the hope that the multiverse might one day leave a trace we can detect. In addition, quantum physics continues to hint at the possibility of multiple realities. Experiments in quantum mechanics, such as those involving entanglement and superposition, show that particles can exist in several states at once until they are measured. Some interpretations suggest that these states are not destroyed, but instead become real in separate branches of the universe. If this is true, then every moment could be spawning countless new realities, each one branching from the previous one like the twigs of an infinite cosmic tree. Even though the multiverse might never be directly observed, its influence on modern science and philosophy has been enormous. It challenges our understanding of existence and raises deep questions about the nature of reality. What does it mean for something to be real if there are infinite versions of it? Are we unique individuals, or are there countless copies of us living different lives in other universes? Is free will truly real, or are all possible choices already being played out somewhere else? These questions push human thought to its very limits. Some scientists embrace the multiverse because it offers elegant explanations for puzzles that otherwise seem impossible to solve. Others criticize it for being untestable, arguing that a theory which cannot be proven or disproven belongs to the realm of speculation rather than science. Yet, even the skeptics admit that the multiverse is a fascinating consequence of the theories we already have. It arises naturally from inflation, quantum mechanics, and string theory, three of the most successful frameworks in modern physics. Whether it is real or not, the idea forces us to think bigger, to stretch our understanding of the universe beyond all boundaries. If the multiverse exists, it could mean that creation itself is an ongoing, never-ending process. New universes could be forming right now, each one emerging with its own space, time, and physical laws. Some might expand for eternity, others might flicker out in an instant. Perhaps somewhere out there, another universe just like ours is being born at this very moment, its galaxies still forming, its stars still igniting, its future still unwritten. And perhaps within that universe, another civilization is asking the same questions, wondering if their cosmos is the only one or just one among countless others.